Okay. So, so thanks, Shay, for that introduction. I'm going to be sharing my screen in just a moment. Okay. So, I'm having some issues on my end. Let me share window instead. Perfect. So let me just make sure that everything we need is on the screen. Okay, I would come to that later, but let's just get started with this. Okay. All right. So welcome everybody. We are going to be continuing our discussion on data structures and algorithms today. We are mainly going to be focusing on trees and graphs. So just before we get started, just a bit of housekeeping here. As I'm going to be going through these topics, this is going to be a long session. So we might not have a lot of time to solve problems, but we can discuss them briefly towards the end. If you have any questions, I would suggest you ask them as I'm going through it. That way I can answer it on the spot. And the other thing I wanted to also bring up is that today I will be trying to go through, I will not really be sharing as much code as possible. I will be going through more of the concepts because it's more important to understand the concepts. And the code can actually be written once you understand the concepts and the pseudocode. So without further ado, since we have a long way ahead of us, let me get started. So what are we going to be talking about today? We're going to be talking about trees and graphs. We'll start with the big picture of what we're trying to achieve. Look at the previous data structures we've looked at. Then we move on to trees. So trees is more like a broad concept, and it has a lot of useful applications. But the most type of trees that would be important to us are the binary trees and the binary search trees. Then we go on to tree traversals, graphs, discuss graph traversals, see how matrices can be represented as graphs, do some problem solving. I will share some exercises that you can do after the class, and then I'll also share some resources as well that would help us going forward. Okay. So I think you've met me already. We can just keep through this. Okay. So I like going through this because I want us to have a big picture of what we are trying to achieve and why we are learning what we learned. So recall that I brought this earlier on in our previous classes. When you have a program and that program is about to be executed on the CPU, it's copied from the story to the RAM. And everything the program does while executing is usually from the RAM. And it's important to know that all the data structures you have considered in this course, they mainly deal with how they are created and stored in memory. From arrays to strings to linked lists to hash maps to graph and trees. It's all about how to organize data in memory when the program is running. So recapping the previous data structures we've talked about arrays. And the key thing to the arrays is that the items are stored together in memory. So you can easily find an item, you can find the position of an item, you can easily get an item. Linked lists, on the other hand, they are stored non-contiguously and are linked together through pointers. So recall when I said earlier that we want to store a group of items together, we can either store them together or store them separately. When we store them together, they are arrays. When we store them separately, they are linked lists. But then if we store them separately, we have to find ways to link them together, which consumes some extra space. Now, those are the two fundamental data structures, and all other data structures use an implementation of either arrays or linked lists or both. Now, coming to stacks. Stacks are like last in, first out, and they can either be implemented using arrays or linked lists. Queues are the opposite of stacks, which can be implemented using arrays and linked lists. And then we've dealt with hash tables as well. Hash tables are kind of a combination of arrays, and sometimes arrays are linked lists. And then in terms of heaps, heaps are essentially represented using arrays. That's the major way they are represented. They could be represented with linked lists as well, but we mostly represent them through arrays because the heaps have a very strict property where you can easily get the left child and the right child. And the reason why using an array is efficient for a heap is because the heap has to be a complete binary tree. So you are going to use up all the items in the array. Technically, any type of tree can be stored in an array. But the issue with trees that are not complete is that you end up using a lot of space when you're trying to store that tree. If the items are not allocated sequentially, you end up with a lot of holes in the array. That's why we use linked lists to store trees. But with heaps, that's not the case, because with heaps, it's a complete binary tree. So the items are kind of together. It has a left child and a right child, and you must feed the left child and the right child. So in that case, you can start with an array. So these are the data structures we've considered, and today we are going to be talking about trees and graphs. Now, you can view trees as the trees we'll be talking about today. You can view them as a collection of linked lists, but linked lists that have not just the next pointer, but they have multiple pointers. And then the graphs are like representing any arbitrary thing in memory, anything you want to represent. It doesn't necessarily have to have any structure. So if you look at arrays and linked lists kind of have a structure. You know, with array, you have the first element, the second element. With linked lists, you have kind of the head, the tail, and then with stacks, you kind of have the head, you kind of have the tail. With queues, the same thing. Those have a structure. With heaps too, they tend to have a structure. But when it comes to arbitrary trees or graphs do not have a structure. They just represent anything in memory that I want to represent. Okay, so let's move on to trees. So what are trees essentially? So like I said, if you have any question, please raise up your hand and interrupt me. I believe that question should be answered on the spot so we can clear any doubts. If it's taking too much time, we can then continue to the end of the session. So trees are similar to trees in real life, in that you have the root of the tree, and then the tree grows from the base. But in computer science, we kind of have them inverted. They grow from the top. And there's also a notion of parents and children. And so if you just think about it, what are the various ways you can represent a tree? You could have like a family tree, like when you're showing your cousins or your parents or your grandparents, or in an organization, when you have like the MDCU, the managers and the employees. So those are ways we can represent, we can use trees in the real world. And then also the document object model for web programmers, those of you that are very versatile with web programming, the DOM is essentially a tree. The HTML DOM is essentially a tree. With the HTML at the roots, and with all the other leaves as children. With all the other nodes as children of that. So this was an example I was saying earlier. So if you look at this now, this is kind of like a taxonomy of animals. You can see this can be represented as a tree. Now, one thing you need to understand is the tree has an order. The tree always has a root. And every other thing stems away from the roots. That is a key property of trees. Then look at the HTML DOM. This is a simple HTML page, and this is how it's represented in the tree. So even in your languages, your compilers, your interpreters, they use a form of tree representations to represent your code when they're passing it. So trees are very, very versatile in computer science. They're very, very versatile. And they have a lot of uses. With a file system, for instance, the file system can be viewed as a tree. essentially. So it's a tree with the root directory and directories with the root directory, and every directory within the root directory is a child of that tree, and they could have multiple children till we get to the nodes. And you can view individual files as the leaves of the tree. But in this case, it's not viewed that way, but if you can represent like maybe directories as nodes as within the tree, and then the files are the leaves of the tree. So what again, going back, a tree is just a data structure that's made up of linked nodes. So if you notice, these nodes are linked to each other. The only difference is now we don't have a concept of next or previous. It's more like, okay, you could have multiple children. So you can see it as a linked list, a collection of linked lists. So usually they're made up of linked nodes, and each node can link to any number of children in a tree. But the key thing is that every node must have one parent node. So a node cannot have two parents. And the root parent doesn't have any node. The root node doesn't have any parents, which is kind of obvious. But majorly in terms of, in the context of what we are learning, we'll mainly be discussing binary trees and binary search trees. So this was what I was saying earlier. We have a root node and we have a child. But in this case, we can see that the number of children we have are arbitrary. The root node has 2 children. The child 1 of the root node has 3 children. Child 2 has 1 child. So the nodes that are at the base that don't have any children, you can refer to them as leaves. So leaves are at the end of the tree. So going back to the example I said about files and directories, files can be seen as leaves if you want to model it like that. Or in an organization, someone without reports could be seen as a leaf of the tree. Okay, so any question on trees so far before we go on to binary trees? Okay, I assume we are all still happy. No questions yet. Oh, okay, I was wrong. Go for it.
What's a node?
A node is an item in the tree that could have a left child or a right child, though that could have children or could have no children. It's just a way to represent data. Like if you think of linked list nodes, you can think of them as being the same thing. Now, within a node, you can store anything you want to store within a node. The node could store maybe data about names, it could store objects, it could store anything. But it's just a way to represent what items are in the tree. And each node usually has different pointers to children. Does that clarify your question?
Yeah, thanks.
Okay. Let me look at the queue. I think multiple people have raised up their hands. Obiano, you go for it.
My question is, if nodes do not have children, then they become lists themselves, right?
If a node does not have it, if nodes do not have
Like
children,
the base here, yeah. Like the
so if a
base
node,
node 3, node 4, 5, and 6. What are they now?
okay, so they are also nodes. It's just that they don't have children. But they are still nodes because within a node, you could have a collection of pointers to the children. It's just that now those pointers are pointing to null. It's not showed in this. I didn't show it in this diagram. But you can view of those nodes as having pointers to null children, which don't exist.
Okay.
So the structure of the node is consistent from the roots to the leaves. It's just that at the leaves, the pointers representing the children are null.
Okay. The root, you said from the roots to the list or the list. Is it LIST you mean or LEST?
Oh, I mean the leaves, like the leaves of the tree.
Okay. All right. Thanks.
The leaves of the tree, yeah. So the leaves of the tree are usually the nodes that do not have any children. That's what the leaves of the tree basically respond to. Okay, so I assume I can move forward now. Did somebody raise up their hand? Okay. Yes, so I meant I'm looking at the chart. So yes, I meant leaves, yes. So let's move on to binary trees. So what are binary trees? Binary trees are a variation of trees. Now I said trees could have children, right? Now in binary trees, they don't have more than two children. That's the key distinction. That's what distinguishes a tree from a binary tree. It never has more than two children. So there are different kinds of trees. You have ternary trees that cannot have more than three children. You can have 2, 3, 4 trees that cannot have more than 4 children. So trees can be restricted by the number of children they have. But for the purposes of what we are learning, we just restrict ourselves to binary trees with 2 children, with no more than 2 children. Okay, so a binary tree is just a specific category of trees, and a binary tree node can have 2 childs at most, 2 children at most, as 2 children nodes at most. So, for example, now this is a binary tree node. We can see in this case the root node is 2, and then 2 has a left child to 1 and a right child to 3. Now, if you can kind of look at the path between 2 and 1, you can see that that's a linked list. And if you look at the path between 2 and 3, that's a linked list. So you can kind of view a tree as linked lists that go from the root down to the leaf, but different linked lists that could intersect at different points and could share different nodes. That's a way you can visualize the tree. So essentially, you have the node, and the node in this case has a value, and it has a left child and a right child. That is essentially what a binary tree is. Now, a binary tree could have 1 child, it could have no children, or it could have 2 children, but it never has more than 2 children. That's the restriction. Now, a heap is the binary tree because heaps do not have more than 2 children when we studied heaps previously. So some properties are, it's non-linear. When I mean non-linear, in the sense that we have a lot of like branches. It's not like we have one sequence from beginning to the end. We have a collection of sequences, which now result in a lot of branches. Hierarchical. So hierarchical means that there has to be a root node. There has to be a node that is a reference that's called the root node. That's what it means by hierarchical. Then a cyclic means there are no cycles. Now, when we talk about graphs, we'll see the implication of when cycles occur. Because with graphs, essentially, a tree is a type of graph that does not have cycles. You can look at it that way. While a graph is a tree that can have cycles. So Nancy says, so class node is the root node. So class node is what we use to store the nodes. Any type of node we are storing is just a class to represent what the node represents. So it could be the root node, it could be the child nodes, it could be any node. It's just a way to represent the nodes. Does that answer your question? Okay. Okay, perfect. Can you go for your question, please?
Yeah. So you said the binary trees cannot have more than 2 children. Is it safe to say that from your illustration here, the root dot left node, that's 1, can it have 2 children, or it stops at that place?
Okay, so this diagram is a simplified diagram just to explain the concept. But yes, one could have children, and one's children could have children, and those children could have children continuously till we get to a leaf. So it's just a way to simplify what a node represents. That's why I did it here, to see how you construct a node from two. So this is looking at it from 2's perspective. Now, 1 could have children, 3 could have children as well.
Yeah, okay. Thanks. I get it now. Thank you.
Okay. Abianu just says, for each not more than 2, correct? Each not more than 2, yeah. Okay, we have our binary trees now. So one thing I want to also clarify is that trees are recursive structures. So if you look at a root node is a tree. The left child of a root node also comprises of a tree. The right child of a root node comprises of a tree. And those trees comprise of trees as well. So you can see that trees can be defined recursively. Same thing with graphs. If you have a graph and you remove a node, it becomes a smaller graph. So most of the data structures we see can actually be defined recursively as well. Okay, so let's move forward. So this was what I was talking about. So we have a root node. F is our root node in this case. we see that G is a child node of F. So child nodes are basically nodes that have a parent, and they exist everywhere apart from the root node. So you can think about it like every other node that is not the root node is a child node. Because if it's not the root node, it has to have a parent. And the fact that you have to have a parent means it's a child node. So is each node a tree? Yes, each node can be considered as a tree. Because the reason why it can be considered as a tree is because each node could have children. And if a node has children, then that is a tree in itself. That's a subtree. Is each node a tree in itself? Yes. You can think about it that every node is a tree. And the exception will be leaf nodes that have no children. Or in that case, you could think of them as having children that are null. So yes, you can think of them as a tree. Okay. Okay, perfect. So we have our subtrees. So we can see F has two children, B and G. But B is also a subtree. And G is also a subtree of its own that contains G and H. Then we have the leaf nodes. Leaf nodes have no children. And leaf nodes are important because that is where we stop processing the tree, because we don't have children from the leaf node. And then the connection between the nodes are what we call edges. So this is a key term I want you to understand. Nodes are what we're storing, edges are what connects them together. So this is it for binary trees. Let's see what's next. Okay, so in terminology, what's a node? The fundamental part of a tree that holds values and links to other nodes. Then an edge is a link, a reference from between two nodes. So Nancy says, what's the difference between subtree and a child node? So the child node is a subtree. Yeah, the child node can be seen as a subtree. Isioma, you have a question, go for it.
Okay, so yes, from this diagram, the previous diagram,
Sorry.
yes. Yeah, so I see that G has a child node I, and then I has a child node H. So when Mr. Soji explained the concept of hippifying last week for binary trees, he explained that trees are filled in from top to bottom, left to right. And for something to be called like considered a balanced tree, like it has to be filled in that order. So I had assumed, or the understanding that I had is that before the sub nodes can begin to have children in themselves, their parents must be balanced in the sense that G must have complete two children before I can begin to bear its own children.
Okay, that's a very good question. So the key thing to understand is that the type of trees that Mr. Soji described last week was a heap, not a generic tree. Now, a heap is a special type of tree, which is called a complete binary tree. Now, for a complete binary tree, you can't fill nodes unless every parent nodes are filled up. That's what a complete binary tree is. So this tree is not a complete binary tree, and this tree is not a heap. So those rules don't apply. This is just talking about binary trees in general. Okay, perfect. So does that mean leaf nodes are like base function? Yes, you can look at leaf nodes as your base case during recursion. Yeah. So okay, so any other questions on binary trees? Please get these concepts down because it's gonna get tougher as you go on in terms of the type of trees to be considering. So there are many types of trees. The heap is one type of tree. And it has some restrictions, which we discussed last week. I won't really be going into that. But it's a complete binary tree. And it's stored with an array because it's complete and it doesn't have a lot of holes within it. So in terms of balancing of trees, I'll talk about balancing of trees later. But essentially, the problem with trees is, I'll talk about that later. Let's go sequentially. Okay, so what's the root? The root is the topmost node without any incoming edges, which is F in this case. What's the parent? The parent is a node that links to another node. So you can think of every node apart from the leaf nodes are parent nodes. A child node is a node that has a parent node. So that means every node apart from the root node is a child node. A leaf is a node that does not have any children nodes. That's straightforward. And now, the concept of siblings, you can look at siblings like the way it is in the real world. So B and G, for instance, are siblings because they are children of the same parents. And you can think of D and I as cousins. Is that right? So your cousins, yeah. So D and I are cousins. A and D are siblings. D and I are cousins. So it's kind of similar to how it is. It gets complicated if you have a lot of branches, but then a subtree is a group of nodes and edges consisting of a parent and all its descendants. So the root node itself is a tree. The root node's children are subtrees, and on and on and on. So you get to the leaf node, which is the subtree of itself. So okay. So another key point to understand is the height and the depth of a binary tree. So the height of a binary tree is essentially how tall the tree is from the base. And the depth is kind of the opposite of the height, how deep it is. So you can see that F is at level 0 because it's the first level. G is level 1, ADI is at level 2, level 3. So the concept of levels, height, and depth, they're kind of synonymous to each other. I won't really focus too much on getting it exactly as far as you understand what they mean. In questions when you come across it, they will define what they mean in that context. Because some start from 1, some start their leveling from 0, some start from 1, depending on how they frame the questions. But yeah, so the level is the number of edges on the path from the root to the node, and the root node is always level 0. It's kind of like you're taking the trees one step at a time, and you're seeing who is at which level and which level and which level. So if you look at it from an organizational chart point of view, you can have maybe the owner of the company at the top and then the subordinates at different levels. So the people at the lowest level are kind of like least significant, something like that. So the depth of a node is essentially the number of edges it takes to reach the node from the root of the tree. So for instance, if you look at G here, the depth of that node is 1 because it takes 1 edge to get to G. The depth of I is 2 because you have to go from F to G and from G to I. Let me see. Then the height of the node is the maximum number of edges on the longest path from the node to the furthest leaf. So in this case now, if you look at F is a height of 2 because the furthest leaf from F is A. Sorry, let me clarify that. The maximum number of edges from the node to the furthest leaf. So let me see. So I take that back. F is a height of 3. F is a height of 3 because the furthest leaf is three edges away. So you can kind of think of it as counting the number of edges, not necessarily the number of nodes. Because you count the number of nodes is 4, but you count the number of edges is 3. So depending on the question, I won't really focus too much. I won't really focus too much on what they're referring to, what they're referring to in terms of. I won't really focus much on what is the leaf or what's the depth or what's the height. I will just really focus on understanding the general concept. Okay, so now, do we have any questions on binary trees before we go on to binary set trees? Okay, go for it.
I didn't get the levels.
Oh, so the levels are grouping of the nodes from the root node. So the root node is at level 0. The children of the root node are at level 1. The children of those children are at level 2. So it's just like you're going from one level to the next level. So that's the definition. Number of edges on the path from a root node to a node. Well, it corresponds to how far a node is from the root node. You can think of it that way.
Okay, so if I was given an assessment now and I was asked what's the depth from, I don't know, how do I, because I can't do that. I've not gotten how that mathematics, how do I get, what's the level from F to I or I to G? So how do I do that?
So I is at level 2. F is at level 0 because F is the root node. But I is at level 2 because it's a distance of 2 from the root node. So you can think of it as the distance between that node to the root node, if you try and go back to the root. So from I, you have to go to G, and then from G, you have to go to F. So that's 2 levels.
All right, thanks.
Yeah. I don't get the height and depth explanation. So the height is, so the height of like the height of the node is how far did that node is from the furthest leaf. So if you look at node, say, let me see now. So if you look at node I now, for instance, the furthest leaf from I is H in terms of its children. So the distance between I and H is just 1. So that's why I has a height of 1. And B has a height of 2 because from B, for you to get to the furthest leaf, you have to go to D and E. So the depth is kind of the opposite of the height in a way, if you think about it. The depth is how deep that node is from the root. So depth and levels are kind of the same thing. It's just that levels start from 0, depth starts from 1. You can think of levels and depth as almost the same thing. So is there a difference between height and depth? So height is just looking at it from the bottom. Depth is looking at it from the top. But they are synonymous. So the question, whatever question will specify what they mean by height and depth, because I've seen different conventions used to refer to them. But the most important thing is to understand that, okay, there is the distance from a node to the root and the distance from a node to the leaves, if that makes sense. So what's the relationship between levels and heights? So levels and depths are almost the same thing. You can look at it, you can look at depth being 1 plus levels. Then the height is looking at it from the perspective of the leaf nodes, not from the root node. So instead of looking at it, how tall are you? You measure from the bottom, right? That's your height. How deep is this? You go from the top and go down. So depth is going down, height is going up. Okay. I hope that clarifies. Okay, perfect. So binary set trees. Questions before we head on to binary set trees? Okay, perfect. Okay, so question. So height will be bottom up and depth will be top down. Correct. You can look at it that way. So what is a binary set tree? Now, a binary set tree is a type of a binary tree. Now, but the binary tree it's actually a binary tree, but it has some other restrictions, which is that all the nodes in the left subtree of that node must be less than the current node's value. And all the nodes in the right subtree of that node must be greater than the node's value. And each of the left and the right subtrees must also be binary trees, must also be binary set trees. I know that's a mouthful, but essentially, think of what we do when we do binary search, right? When we do binary search, okay, we've not discussed binary search, so I'll skip that for now. But binary search trees, and essentially, the idea is, if we are at a node, we should be able to know the nodes that are less than that node and the nodes that are greater than that node. So every node to the left of that node is going to be less than the node. And every node to the right of the node is going to be greater than the node. Now, that also applies to all the children continuously. So essentially, so for example, now this is a BST. Now, if you look at this binary set tree, look at 25 as the root node. You would notice that every other node in the left subtree is less than 25. And every other node in the right subtree is greater than 25. This is essentially what the binary set tree means. And the reason why it's called a binary search tree is because we want a binary tree that we can search through. And the idea is we want a binary tree that we can search, right, without having to look at all the nodes. I remember when I talked about like doing binary search, the idea of splitting a problem into two, or splitting a problem into two parts and going down one path, that reduces the problem to a logarithmic problem. So essentially, the reason why it's structured like this is they want you to be able to search for things in logarithmic time. Now, so if you recall, when we talked about hash maps allow you to retrieve items in constant time, right? Now, but the problem with hash maps is that you can't order them. You can't search for an item in the hash map without going through the entire hash map. You see the thing? So, but with binary search trees, right? With binary search trees, you can have a hash map based on a binary search tree that allows you to search for items in log n time and be able to retrieve and get items in log n time. So essentially, if you want to retrieve an item, you just search for it and retrieve it. So that's the essential of, that's why the binary search tree is important. So if you notice, the hash map does retrieval in constant time, but it does searching in linear time. The binary search tree is kind of like a compromise between the two approaches. Yeah, okay, instead of having one constant time and one linear time, let's have both logarithmic time. So a lot of like data structures in your language is like a tree map in Java is binary, is a variation of a binary search tree, essentially. Anytime you have like a hash table or a tree in your languages or anything, is a variation of a binary search tree. So the main reason why we have this restriction is because we want to be able to search for items. It's key to understand that. And once you understand that, you understand why the items to the left are less and the items to the right are greater. So I have a question here. It says, what happens when there's a node with an equal value as parent? So I think your question here is saying, what happens when you have duplicate values, right? So when you have duplicate values, which you usually don't have, then there'll be a convention of whether to store the duplicate values on the left or on the right. So the left will contain nodes that are less than or equal to, and the right can contain greater than, or the left will contain nodes that are less than, and the right will contain nodes that are greater than or equal to. Or you could have them stored in the same node. It's a list, depending on what you're storing. So that is the detail that I won't worry too much about. It's important to understand that everything on the left is less and everything on the right is greater. Okay, I think message for the admin is there. Okay, so will the values always be sorted? So in the tree, yes, the tree. So it's, if it's in a binary set tree, it's kind of sorted, but it's not sorted in terms of linear sorting. It's sorted in terms of a tree structure. So as you insert items to a binary set tree, yes, they will be sorted. They will always be sorted. In that you can easily find them in log n time instead of linear time. So you can look at a binary set tree as allowing you to use a link, because if you look at a binary set tree, it looks like a linked list. Each of the parts look like a linked list. Like if you look at the part from 25 to 20 to 19, that's a linked list. 25 to 20 to 23 to 21, that's a linked list. Like that. So you can look at it of allowing you to search through, like search through like a linked list easily. A collection of linked lists easily. I'll do some visualizations later so that we kind of get the idea. But so there's an exercise, anyway, we'll talk about that later. So I'm going to have exercises for us now. We are going to look at some examples and we'll determine if they are BSTs or not. So what do we think? Is this a binary set tree? Okay, thumbs up, yes, thumbs down, no. See, most of us are saying no, some of us are saying yes, some of us are saying no. So the reason, so if you look at the definition, right, this is confusing, but the key thing that the reason why it's not a binary set tree is because it has 3 nodes, and a binary tree must have at most 2 nodes to begin with. So that's why it's not a binary set tree. Does somebody have a question? Okay. So is this a binary? Go for your question.
Yeah, did you say is not?
It is not a binary set tree because it has, because node 20 has 3 children, not 2 children.
Not 2.
Yes, it has 3 children, and a binary set tree, because it's a binary tree, you can have at most 2 children. Is that clear? No, so a binary set tree can have at most 2 children. not at least two children, at most two children.
Okay, so like this left hand now,
Mhm.
um, I don't get it because
Okay.
the other one you showed now has, as the subtree. That's
Mhm.
two. Yeah.
Mhm.
Mm-hmm. Okay, now I get it. So coming down, it still has two children.
Mhm.
Okay.
Mhm.
Okay. Okay. I see. All right, I see
Mhm.
it now.
Okay. Perfect.
Mm.
So the reason why this is not a binary section is because it had two children. If you took out this one of the 23 nodes, then this would become a binary section. If you took out one of the 23 nodes. But because it has three children, it's not a binary section. Okay, so are we clear on this? Okay. Moving. So there's a question, what about the right subtree? So the right subtree, so this is the thing. When we say, is this a BST, we are looking at it from the perspective of the root node. All right. So yes, node 30 on its own is a binary set tree. But node 30 on its own being a binary set tree is not sufficient. Every node here has to be a binary set tree, has to reach the condition. But 25 does not meet the condition because 20 doesn't meet the condition. So that's why it is not. But if you look at just the right subtree is, but it's not sufficient for the entire tree being a BST. Does that clarify? Okay. Yeah. So is this a BST? It's a tricky one, but yes, it can be a BST. So in this case, they might have defined that the left subtree is the left subtree can contain values that are less than or equal to. So in this case, yes, that's perfect. That's fine. Now it doesn't matter which convention you choose, as far as they are consistent with whatever convention you choose, it should be fine. Yeah. Okay, so I think this is clear. We can move on to the next now. Okay, is this a BST? So quick caveat: assume that every pointer is a right child, not a left child. So if you assume that every pointer is a right child, is this a BST? Yeah, it's a BST, right? Now, but you can see this BST now is essentially a linked list. Because yes, it's essentially a linked list. Now, the reason why this BST is like this is it was the order in which the nodes were inserted to the tree. So like 25 was first inserted, then 30 was inserted, then 35, then 40. Now, the issue with this type of tree is if you want to search this tree, right, you have to go through the entire. So let's say we are looking for 40. We have to go through the entire tree, which reduces to a linear operation, not a logarithmic operation. So this is where balanced binary trees come into play. A balanced tree will ensure that the tree is not skewed to the left or to the right. And ensures that the tree is balanced. So the reason why you want the tree to be balanced is because when you are searching for items, you want to be able to eliminate as much items as possible by going to the left or to the right. But if you are going on one direction only and the tree is like a long chain, then your searches become linear, which is bad. So there's a technique they call balancing of trees, and there are different kind of balanced trees I would have. Some of them are AVL trees and red-black trees. They are very complicated, and nobody really cares that details of how they work. Just know that okay, they help you achieve logarithmic complexity for searches, and it helps retrieving balance. That's the most important thing to understand. Okay. So I think there's a question in the queue. Did I miss that? Did somebody have a question?
Yes, I do. Can I speak?
Sure, go for it.
Okay, in the second example you gave for the BST, I noticed that the root had a value of 25 and the left hand side also had a value of 25.
Okay.
My question now is, you said the rule is it's supposed to be less than at the left and right down, but here is an equality.
Yes. So in this case, you can assume that the equality is assigned to the left side. So the left side contains values that are less than or equal to.
And that would
And the
also
right back,
work.
that would also work. Yeah. So you could also
Thank you.
you could also say, okay, equality is on the right side. It doesn't really matter which you follow, but you have to be consistent across all the nodes. Because the key is someone looking at this node should be able to know what direction to go if they are looking for an item. So let's say I'm in the first node 25, right? And I'm looking for another 25. I know that, okay, it's going to be on my left node because it's less than or equal to me. So I just go to the left channel and continue the search that way.
Okay, but can I say, okay, does that mean that if the left node starts with an equal of 25, if I make every other thing under it less than 25, would this still work? Or does the values have to consistently be equal to the next upper, to the subtree above it?
Okay. So the values of a node, all the values in the left subtree have to be less than, that node. All the values in the right subtree have to be greater than that node. So all the values on the left of the 25 that you're going to add have to be less than 25. But the values on the right can be greater, they can be greater than 25, right? But in
Yeah,
this
but
case,
my question is now
but in this case,
on the next sub level, on the first sub level, now we have 25, which is equal
yes,
to our root value. Now, on the next
yes,
sub level of 25, now, can we have a value that is less than 25 and is also less than our root value?
less than 25 and less than our
I'm
root
saying
value.
if the first one is the 25, which is A, and the second value is 25, which is B, if we have another
Mhm,
level C, can the
mhm.
values on C be 24, 23, less than what we have here, consistent with the rule that says the left hand side should be less than and the right hand side should be greater than? Or if we start out with an equal value at the left hand side, should we retain that equality all through and just
Um,
assume that everything on the left hand side is equal and everything on the right hand side is greater?
so yeah, so going back to your question, yes, everything under 25 has to be less than 25. Under the second 25 has to be less than 25. The reason being that it can't be greater than 25 because if it was greater than 25, it would be on the right side of the upper 25. That's the first question. So the second thing is, in terms of like determining your convention, it's just like instead of having less than on the left and right side greater than, you can say less than is left than or equal to. So if it's equal, it will be on the left. It might not be a direct child, we don't know. So there could be a right node now. For the 25 now, there could be a left node that says it's 25 as well for the second 25. But the key thing to notice, we just want to know where to look for in the tree to find whatever we are looking for. Am I answering your question?
Yes, I got it now. Thank you.
Okay, perfect. And if for some reason, after we go back and forth, you feel that maybe I've not answered it, you can always type it in the chat or something.
Okay, sir.
Okay. So this is okay. So we are here. We're good with this, and now this. Okay. Quick question. So I have a couple of questions. It's a linked list could also be a binary tree. So if a binary tree is skewed to one side, it reduces to be a linked list like this. If a binary tree is skewed to one side, it could be skewed to the left or skewed to the right. It reduces to be a linked list. I think I should have some visualizations coming up, but let's finish with this exercise to explain this concept more. A quick question. I thought if there is no sorting of items, the time complexity automatically becomes logarithmic. If there is no sorting of items, I'm not sure I understand your question. What do you mean by no sorting of items? So if you sort items, then the time complexity becomes logarithmic. Okay, go for it, Nancy.
Hi, can you hear me?
Yes, I can hear you.
Okay, so I was asking, so since um
the if it's a linked list, right, and it's already
Mm-hmm.
sorted, so we don't need
Mm-hmm.
to sort again. So it's supposed to be it's not supposed to be a linear time complexity. It's supposed to be a log. Is it log what? Can you pronounce it for me? I'm having issues pronouncing it. But I
Logarithmic.
thought exactly. So I thought if it's already sorted, like you don't need to sort it again before solving the issue. I'm not trying to say
S-
somebody but understand what I'm saying. Like I'm confused.
so I'm
Like
trying
now,
to get. Okay.
since okay, let me structure my words correctly. So I thought like if it's a linked list and it's already sorted
Mm-hmm.
30,
Mm-hmm.
40, 50, and we don't need to sort it again,
Mm-hmm.
right? It's
Mm-hmm.
supposed to have a constant time complexity.
Constant time
Like
complexity for searching. For searching.
yeah, exactly for searching. So like this one now, if I'm searching for 35 now, I will know that
Mm-hmm.
we can just divide the list. So if 30 is greater than like if the number we are looking for, the value we are looking for is 35, and we know that 30 is already less than 35, we can just move to the next value. It's already sorted,
I
right?
think I get your question now. I think I get your question. So the key thing here is if this was an array, mm, then you are correct. Because the key thing with that, with an array, you can jump to different positions. Like if you're in the middle, you can jump to the left or to the right. You can easily jump to any index. But with a linked list, that's not the case. You have to go, you only have access to the head and the tail. So it doesn't matter if a linked list is sorted or not, it's still going to be linear because you can't know where the middle is without searching the whole list. See the problem.
So how do you determine the time complexity like for this now? Like I want to know how to determine the time complexity when you're solving a question like an algorithm, like how to know which one is linear, constant time, whatever.
Okay.
You
So in
understand?
terms of knowing, yeah, so in terms of knowing the time complexity, you think of the amount of work you're doing with respect to the input. So in this case now, the input is a tree. This is the tree is our input. So let's say we are searching for an item here, right? Naturally, if we are traversing a tree and we are going through a path, we can only go from the top to the bottom, right? And that is actually the height of the tree. But in this case, the height of the tree is very long because it's skewed. So the time complexity is the height of the tree. But because it's a skewed tree, the height of the tree is also n, which is number of nodes. If it was a balanced tree, the height of the tree would have been log of n. If it was a balanced tree. So in this case, to know what time complexity you are, you have to analyze what you're doing. Like analyze what the work you're doing with respect to the input. That's how you know the time complexity. Does that clarify your question?
No, I don't understand
You don't understand.
at
Okay.
all. I don't understand at all.
Okay, how do we do this now? So what part of it do you not really not understand? Is it the concept of the trees or the concept of the linked list or sorting or searching? Which of them is not clear?
No, I just want to know how you're able to determine the time complexity for this particular one. Like the way you just said it, it was easy for you, but I was just trying to like understand the logic behind the time complexity, right?
Okay.
So if you're
So
like to implement a search algorithm here now, how do you know the time complexity for it?
okay, so with this type of data structures, the time complexities are usually fixed. Like for a tree, when you are searching a tree, it's the height of the tree. That's the time complexity. Now, the reason why the height of the tree is because, so let me go back to a previous example now. So let's say we are searching for, this is a BST now. Let's say we are searching for any node in this tree. So let's say we are searching for 23, for instance. The only node we have access to in the beginning is the root node, which is 25. So we'll go to 25. We check 23. 23 is less than 25. So we'll go to the left. By that, we've discarded the entire right. We come to 20. We are looking for 23. 23 is to the right. We see 23. So if you look at it, searching for any node, the maximum amount of time you will take is the height of the tree, which is the length from the root to the furthest leaf. So the time complexity is the height of the tree. That is the time probability for searching a binary set tree. Now, but if the binary set tree is not balanced and is skewed, the height of the tree is the number of nodes in the tree, like this one here. We have 4 nodes and the height of the tree is 4 because it's not balanced. So that's why it becomes linear in this case when we are searching for an item. But normally it should be logarithmic. It should be the height of the tree, which is logarithmic if it's balanced. So that is the reason why we always try to balance trees we use in real life, because we want to prevent this kind of situation where you are skewed to the left or you are skewed to the right.
Okay, thank you. Thank you.
Okay, if that didn't clarify, you can pick it up offline.
Okay, no problem. Thank you.
Yeah. Okay, so question, I think we are sorting it while we are adding it. Yes, a binary set tree is implicitly sorted while you're adding it. Sorted in the sense that you can easily retrieve an item in logarithmic time. So BST are logarithmic because you don't have to search all the nodes to get what you want because of the rules. Yep, correct. Yep. So is this a BST? Folks are not sure, or we are waiting for other folks to say if it's a BST or not. Okay, that's fine. So yes, it's a BST. It's a BST. In this case, it's number, but this is a BST because if you look at it, it satisfies all the conditions of a BST. Okay, is this a BST? For folks that say yes, I will look closely again. So it's not a BST because of the cycle, because there's a cycle in this tree. Yes, the link across makes it not to be a BST because it's what's the problem. The reason why it violates the BST condition is 2 things. 1, there becomes a cycle, and 2, D has 2 parents, which is not allowed in a tree. In fact, this is not even a tree. Not even a BST. This is not a tree to begin with. Because in a tree, you must have 1 parent. A parent could have multiple children, but all children must have 1 parent. That's the definition of a tree. So this is not even a tree, regardless of a BST. So is this a BST? Yes, it is a BST. Folks that said it's not a BST, why do you think it's not a BST? So it's a BST here because it satisfies all the condition of a BST. Now, there's something I want to point out here. If you look at nodes to the right of 20, all right, nodes to the right of 20, right, they should be greater than 20. But remember that because 25 is its parent, those nodes have to also be less than 25. So you discover that everything to the right of this subtree of 20 is going to be less than 25. That's one thing I want you to get here, because the law applies to not just the direct children. All the children recursively have to also satisfy the law as well. So remember when we did heaps, it was just comparing the left child and the right child. But in this case, it's the entire subtree, not just the left child and the right child. Okay. Do you have any questions on this? Do you have any questions on this? Okay. So to represent the BST, the same thing as we had to the binary tree. Essentially, it's the same thing in terms of the representation. There's no difference. Yeah. So there's no difference. It's the same thing in terms of the representation. There's literally no difference here. It's the same thing as the binary tree, basically. So usually this is how you have a BST class, a BST. Usually So the key things you want to do in a binary search tree, you want to insert an element, you want to find an element, and you want to remove an element. Those are the core items in the binary search tree. So thinking of how I said when you are looking at data structure, to think of what you're doing in data structure. You think of how do I get items in? How do I take items out? And how do I find items? That is the core of most data structures. For arrays, how do you insert? How do you take out? How do you find? Linked list, the same thing. Keeps, the same thing. So with all these data structures, you see, like some make it easy to insert, some make it easy to remove, some make it easy to find. But the BST is kind of like a compromise between everything. For instance, an array makes it easy to insert. It makes it hard to find unless it's sorted, and makes it hard to remove. A linked list makes it easy to insert, makes it hard to find, right? And makes it hard to remove. A hash map makes it easy to insert and remove, but makes it hard to find. You see the thing? Now, a heap, right, makes it easy to insert and remove, but makes it hard to find. But binary search tree is saying, okay, let's compromise between everything. Let's make it not too hard to insert, not too hard to find, and not too hard to remove. So it's kind of compromising between all these operations to make it balanced. And logarithmic, and everything being logarithmic is actually okay, because logarithmic is almost as good as constant in some cases, in most cases. So this is why the trees are very, very important. So someone said, the one you showed with letters, what makes it a BST? Okay, so the letters are, you can look at the letters as like being sorted, like A is less than B, and B is less than C, and less than D, less than E, F, G, H, like that. So if you look at it and replace it with numbers, you will see that it's a BST. So essentially, we are treating the numbers like letters, like numbers, like sorted. Like we are treating the letters as sorted based on their order in the alphabet. Does that clarify? Okay, perfect. So moving on. Okay, so to insert into a BST, what do? We put a node into the BST, right? To find, we find a node in the BST, and to remove, we remove a node in the BST. Those are the three things we do. And if you want to insert, I will take us through this thing later. But let's look at this visualization quickly. Okay, so this is a binary search tree, for instance. Let me create a tree. Let me just create a tree with 5 nodes, random. Now, this is a binary search tree. Now, but if I make it skewed to the left, you see this. If I want to search for an item, I have to go down. Oh, it's not big enough. If I have to search for an item here, so this is skewed binary search tree. You can see that searching a skewed binary search tree is bad because it necessarily becomes a linked list. But if you are trying to do the same so if it's skewed to the right, you fall into the same issue here. Because you need to search through the entire list. And at the furthest, you have to go to the last node. And if you go to the last node, you have passed through all the nodes in the tree, which is all of them. But if it's balanced, so for balanced, this is the balanced binary search tree, for instance. You can see it's easy to find items. So let's say I'm looking for 41. All right. What do? I just start from 37. Since 41 is greater, I go to the right. Since 41 is less than this, I go to the left. So at most, I'm going to go from the root to a leaf through a path, which is why it's synonymous to the height of the tree, which, if it's a balanced tree, the height of the tree is logarithmic. It's log of n. Now, you can think of it as looking at what we're talking earlier when I said the height of the tree is log. So if you have 2, right? So if you have the root node, which is 2, if you look at all the children, if it's balanced, you multiply by 2 to add, right? If you look at those further children, you multiply by 2, which is 4. So this is 1 node, this is 2, this is 4, right? The next one is going to be 8. Total number of nodes is going to be 8, and then 16, then 32. So notice that for you to increase the height by 1 factor, you need to double the current items. So that's why it's logarithmic. Because as you are going from one height to another, for the tree to be taller than it is, and it is balanced, right? You have to double what is existing in the tree. And this is an important point to note, because if you look at this tree, for instance, now, if you look at the nodes here, the nodes are four elements, right? If you look at every other element that is not the node, those are 3 elements. So that tells you that most of the nodes are the leaves of the tree. Most of the nodes are the leaves of the tree. So if I add another level here, and I add 8 nodes underneath it, all these items here, right? All the items you see here, they are just 7. They are not up to 8. If you do that again at the level of 8 nodes, right? So let me increase the height to so this is 7, right? So if I want to make this tree have an extra height, that tells me that I have to add 8 nodes, which is 15, to get a balanced tree. Now you see that the height has increased to 3 because I've been able to add double of what was existing. And it's double because each node has a left child and a right child. So for all the current nodes at the base, right, you are doubling it as well. And all the numbers at the base are equal to all the numbers on top of it to begin with. So by the time you add the ones at the base and the ones at the top and compare it to the new level which you've doubled, they are essentially the same. So this is why a tree is logarithmic. Like, this is the key reason why we try to balance trees, because balanced trees are really a big deal. Now, you don't have to know how to balance a tree. It's not really important. It's just important to know that they are balanced. If you are curious, you can look it up, but it's a bit complicated and it's hard to get correctly. But it's important to know that this is how most hash maps in. So any hash map you see that you can sort, any map you can sort, sorted map, sorted sets, anything that is sortable, right, is most likely having a tree behind it, if it's not an array. Any language that has something that is data structure that you can sort, right, then it's most likely a tree. Okay, so what do we have next? So you might be asking, can I implement a tree with a hash map? Yes. So a hash map can be implemented based on this. If the keys are just the nodes and then the values are within the nodes, you can implement a hash map based on a tree and achieve logarithmic complexity for everything. But the thing is that the hash map based on the arrays is constant complexity for retrieval, but it's not easy to find. But this balances best of both worlds. Okay, so are we clear on the tree structure and why it's important to have balanced trees? Emmanuel, go for it.
Yes, I understand how it works, but I'm curious to know, like, what other kind of problems can we solve aside like numbers? Can we use this to like search like a text in a dictionary or something? Like,
Yes.
what other can we use it for?
Okay. So we use numbers because those are the easiest during learning. But technically, any item, any group of items that can be compared, that are comparable, that you can tell if one is greater than the other, you can use to store them. So you can use to store anything. You can use to store students, you can use to store names. As far as you have an ordering of which one is greater than the other, you can use to store it. You can even use to store objects. So typically, like when we use this for, like when I used this to do something, projects in the past, I wanted to store an object in the tree. Like you have to like kind of override the greater than or less than method to know if an object is greater than another object. But you have to define that notion of what is greater and what is less than if you are storing something custom. So anything can be stored in trees. General numbers are just arbitrary. You can store anything in a tree. You can even have a hash map within a node of a tree. As far as you can order the hash map between each other, you're good. I think that this question will be best left to the I think you should contact admins for your question. Hamzat, I think you contact the admins for your question. So let's move on. So now, if we want to, we're talking about searching and finding. So if we want to insert a node into this tree, right? How do we do it? So let me come here. Let me say I want to insert. So let's say we want to insert 50, for instance. What happens? Did you guys see what happened? It went and inserted 50 here. If you want to insert, say, 25, you see what happens? It's trying to find where to insert it. And it inserts 25. So that's inserting. When you want to search, so if you want to search for 25, for instance, it begins to search for it based on the rules of the PST, going either to the left or to the right, and then it finds 25. If you want to delete is a bit complicated, which I wouldn't really want to. I don't want us to go deep into it until we really understand the other things. So I'll just continue from here. So, but these are the key values, and understand that they are logarithmic. So, like I said earlier, to insert is O of log of n, find this log of n, remove this log of n. So a cheat code you can know is that you can look at it in a binary tree or in a binary set tree. Any operation in that tree is log of n. Once you have a tree, right? Whenever you have a tree, you typically can't do constant. If you are trying to remove something, if you are trying to access the roots, that could be constant. Like in a heap, accessing the top node is constant. But if you have to insert or remove something or find something, you can't do better than logarithmic, because you have to go through a path in the tree at the minimum to get what you want. So, like I said earlier, so to achieve log of n, the tree should not be skewed to the left or to the right. It should be balanced. This is key to understand. So, most reward applications use some form of balance trees. And the two common balance trees are ABL trees or red black trees. I just mentioned it there for completeness. You don't really need to bother about this stuff. So this is the pseudocode for find. I think in the interest of time, you can go through this later. It's essentially what it does is it starts at the root node and checks if it's greater than or less than the root node. Keeps going until it finds where you should insert it, and then it inserts it. So this is the pseudocode. I included it in pseudocode form so that folk can look at it in a language agnostic way. I don't want to provide like language code. So insert, for instance, what it does is it creates a node, right? And then it tries to find where to put in the node. Sorry, this was find. So this is find. Sorry, not insert. This is find. Where it finds the node. Insert is the same thing as find, except that you are putting a node in at the leaf where it should be in. Remove, on the other hand, is a bit more complicated because the key thing is you have to find the node to be removed first. And then, because the node you are finding could be anywhere in the tree, it could be in the middle of the tree. So you need to replace that node with some other node, which is one of two things. Either you replace it with the largest to the left or the smallest to the right. And then when you replace it, you now have to delete the node you replaced it with as well. So it's a bit involved, but I won't really focus too much on this because you can learn the implementation, but it's more important to be able to use it to solve problems than for focusing on details of how it's specifically implemented. So that's it about trees. Do we have any question before we go to Traverse House? Go for it.
Thank you. So about inserting values into a tree.
Yeah.
If I want to, for example, insert maybe number 10, and the parent of 10 is maybe on the left hand side of the root, and the parent is of course larger than 10. But there's a value, I don't know how to explain it. Maybe if you give me one of the diagrams that you used before.
Okay, let's do something. So use
Yeah.
use this tree.
Okay.
1 second. Let me reduce the. Let me create a tree with. Let me make the number of nodes 7. Oh yeah. So with this, I think it should be.
Okay.
So ignore the
So
2 here in front of 53. Just ignore the 2. It's not important.
all right. Okay. So now let's say I want to insert 54 into this tree, right? Of course, are you going to remove the current node that has 53 to put in 54 and then make 53 the left hand node of the 54 that I add, or we are going to add it to the right of this 53?
So in this case, you add it to the right of the 53. You never, so when you are inserting, you always insert at the leaves. You don't insert in the middle.
Oh, so there's never a swap, right?
In this case, for binary, so for binary set
position.
trees, no.
Okay.
Yeah.
Thank you.
I get where you are coming from. For heaps, you need to swap. Now, the reason for heaps you need to swap is because you can't have holes in the tree.
Okay.
That's why you swap for heaps. But for binary set trees, you don't need to swap. Now, there is something that they call rebalancing, but I don't want to bother too much about it. Essentially, what it means is when you insert a tree, it tries to figure out how to balance it. I'll give you an example. So let's say we want to insert 54 here, right? You go to the left of 61 because it's less than 61, and we'll go to the right of this. Now you are correct. If we had set this to 54 and set 53 to the left of it, it will still be correct. But it's just easier to just insert it to the right. So let me run through that animation and see. Let me see how I can. Let me try something here. Can I? Okay, I'll make it slow. Okay, so let me insert 54, right? Now we go. So you can see what is happening here. Then it gets inserted. Now that balance factor is just AVL tree trying to rebalance the tree, but that's fine. So now let me start something.
Thank you.
Okay. So if I empty the tree, right, and I start inserting, let's say I start inserting in a very bad way, and I insert 1. I've inserted 1 here. If I insert 2, see what happened. 2 will get to the right. So what should happen now if I insert 3? It should go to the right, right? It should be skewed. Because it will say, okay, 3 is greater than 1, let me go to the right. 3 is greater than 2, let me go to the right and insert it. So let's continue. I want to show you how the rebalancing works. So if I insert 3, same thing. You can see what it did. It rotated the tree so that 2 becomes the roots. So this is essentially what rebalancing is. To keep the tree balanced instead of skewed. So this is what AVL trees do automatically. The mechanism of how they do it is really complicated. So that's why I'm not really going to go into it that much. But they kind of rotate the tree. So if we let me keep inserting 4 now. Insert a 4. Now what happens? It goes here. I think we did rebalance. I don't think it will rebalance. No, not yet. Not yet. Now, if I insert 5 now, it's going to rebalance it. Let's try. Now it's getting skewed. Now it will rotate the tree now and change it. It's essentially the same thing. It still satisfies the BST. It's just like that, reorganize it so that it's easily, you can easily search for things. So that's just the mechanism of rebalancing. It just helps to keep things balanced. But yeah, so that's it about inserting. Search and insert are almost the same thing. In fact, search is the easiest because you just need to go through a path till you find the node you're looking for. So we've done insert. So let's search for 5, for instance. We move, and we come here 5. So I have a question. Say name BSc and how it works. Does it qualify to move from an engineer from junior to mid-level or perhaps to senior? Typically, I'm asking is at what point in one's career will one start having to have a use for BSc as an engineer? So the key thing to know about these things is the reason why it's important to know how they work is because there are some projects you have to select data structures you're going to use to store things. And it's important to know how that data structure is implemented under the hood so that you can get the optimum time complexity. For instance, if I want to store a list of students, right? Students and their scores, right? I could just use a hash map to store them. But if I want to know which student was first, which student was second, which student was third, or whatever the ranking of the students were, I could do it with the hash map and search, but it's going to be slow. But if I use a balanced tree, I can do that more efficiently. So these things are subtle. Like nobody will come and say, okay, implement a BST or code up how a BST works. But the knowledge of knowing how they work helps you select the appropriate data structures to use for the job. That's where it's important. I don't know if that answers your question. Yeah. So I agree. Sometimes you'd be like, okay, why am I learning all these things? Why would I need it? But the thing is, when you're selecting data structures to use for things, it becomes very important. And it could be the difference between writing a fast application or a slow application. So someone has a question, go for it. Yes.
Okay, I don't know if I may, and I don't know if it's like, anyway, it's just a follow-up to Adeshola's question, right? So, like you rightly said, many times you will not be told what tools or what data structures to use to solve a particular problem. And in my experience, with the little experience I've had, it seems as though no one really cares or no one is really checking for optimization. What people want to just know is like, does it get the job done? So many a times, what an array list would do, a hash map will also do it, right? And now with what we are learning, you can see, of course, that a tree will do it as well. But then nobody's really looking. If I still go and do it with an array list, it will still be accepted, right? So, I mean, yeah, it's great that we're learning this though, but so far I haven't actually been in an environment. I've never had an experience where it was like really required of me that, okay, do this or use this particular data structure, and if I didn't do it, then someone really like pointed out that, oh, it's slower or something, or the application is not as optimized as it should be. I don't know if I've made any sense.
I see what you're saying. I see where you're coming from. And I don't know what your background of, like, what your experience has been like, but if you're working mainly from like so it depends on what you're working on, right? When you're dealing with things that have to scale, right, at like the level of which like big tech operates, and all of that and no login is a very big deal. Like it's really, really a big deal. So when you're dealing with, if you have few users, it's not important. If you are just making an API call to pass something or to process something, it's not important. When you have to run a query for millions of users in a database, or you have to store the items in a structure for retrieval later in an ordered fashion, then it becomes very important how you choose what you use to store it. It becomes very important because, like I said, it will work, right? But the issue is that it will be slow. And then users might probably start complaining. That's the thing. So, but in my experience, like during like what do you call it now? During like code reviews and stuff, people really pay attention to these things to see, okay, is this optimized, is it efficient? Now, not to the level of granularity of, okay, maybe we must make this like O of log n or this, but we have to just make sure that it's acceptable enough for what the user expects. And when you are dealing with large data, it's the differences between what you use matters. So I shared something in the first class we had about this guy that maybe I didn't share, but someone was running queries basically and was discovering that their queries were taking too slow. And it was because they were doing a quadratic loop instead of a single loop. Because they didn't understand how that data structure was storing things. So yes, it will still work, but then it now becomes an issue of how acceptable is the performance for the users. Dealing with a small data set is not a big deal, but when you start thinking of like large data sets and you start thinking of a problem that's scale, then it becomes a very big deal. If you're working in infra, maybe in DevOps, you might not really encounter this level of intricacies. But it also depends on where you work, what level you work at. If you work at like an operating systems level, like people that write all this OS code, they deal with a lot of all these data structures. If you work in implementing databases, they deal with all these things. But for our perspective as like engineers, what we just need to know is we don't really need to bother about the details of how it was implemented and try to re-implement it. We might do that to understand it. But what's important is being able to select the data structure for the right purpose. That's the most important thing. Yeah.
All
So
right, thank you very much.
yeah. So in terms of delete, maybe I should just put delete so that we understand how delete works. It might be a bit involved. So if you remove, let me find a troublesome one to remove. Let me say we remove 2, for instance. Now this is what will happen. It sees 2. It looks for the largest to the right and replaces it with 2. So you can go through, you can use this visualizer and play with it. It's important for you to understand the process. Then when you understand the process, you can now look at the code behind it. Well, I included the pseudocode here as well, just for us to be able to follow along. So there we go. I think we're done with trees and we are going now to tree traversals. So for tree traversals are essentially how we want. So if we have a tree, I want to enumerate all the items in the tree. There are different ways you could go about it. The 2 main ways are either breadth first search or depth first search. And those are the 2 I'll focus you really know well. In terms of like interviews, I know depth first search and breadth first search are kind of they are the most popular. Now, a breadth first search essentially means you start at a node, right? And then you evaluate the nodes that are closest to that node before you go to the nodes that are farther out. So we have this now, and we are going to go through visualization to see how breadth first search works. Okay. I think this is legible enough, right? So a breadth first search can also be seen as a level order traversal, which means that it goes level by level. So now, if we want to traverse this tree using breadth first search, right? We start at the root node. So watch. We put it to the queue. So one thing to notice is that the breadth first search uses a queue, like I said when we're doing the queues. And the depth first search uses a stack, which could be recursive or iterative, but we'll get to that. So now it pushes it to the queue. Now, this is the only item we know in the queue. Now, it then looks at the first item that's pushed to the queue, takes it out of the queue, and says, okay, from this item, what are the neighbors I have? So it has B and G. So it adds them to the queue, right? And then goes to B and asks, okay, what are B's neighbors? B's neighbors are A and D. It adds them to the queue, right? And then goes to the next item in the queue, which is G. Now, notice that even though we have FB, even though we have A and D in the queue, we still go to the one that is at the same level with B. which is why it's called breadth first search, in that it starts from the where we are starting from, and it kind of radiates out from there. So the closest nodes gets expanded first, and then the outer ones like that goes out to the end. So now we have G. Now, when we come to G, G has only I. You put I to the queue. The next thing in the queue now is A. So we take out A from the queue. Right? We take out A from the queue. But A has no children. So we just ignore A and go to the next one, which is D. D has C and E. We add them to the end of the queue. Right? Now, the next one we are going to take is I. Notice the level at which it's taking them. It's taking them for the top to the next level to the next level. When we go to I has H. So we add H to the queue. And then we take out C. It has no children. We take out E. It has no children. And we take out H. It has no children. And that's our breadth first search, basically. That's how breadth first search works. You start from the node you are trying to search, and then you go outwards, but you expand the closer nodes before you expand the outer nodes. Depth first search is the opposite. It goes depth first, but this one goes breadth first. So is this clear? Thumbs up, thumbs down. Okay. So for those that are not clear with breadth first search, you can ask your question. But essentially, it starts from each level and goes to the next level. Any questions before we move forward? Okay. So let me go back to. So this is essentially the breadth first search equivalent. Now it's important to note that. Okay, not now. We'll talk about that later. So this is how the breadth first search algorithm works. Now, so this is pseudocode. Essentially, you create a queue, then you add root node to the queue. Then while the queue is not empty, you keep removing items from the queue and add their children. So for each node in the queue, you take out a node, you perform whatever operation you want to perform. This is the business logic you might want to perform, like maybe you want to print it out, or you want to store it somewhere, or you want to do anything. Then if the node has a left node, you add the left node to the queue. If it has a right node, you add the right node to the queue. So this is essentially how, and you can, if you think about it in terms of breadth first and queues are kind of fair in that the first person to get in, the first person to get out. So if you are starting from a point and you want to find people, it's only fair that you find people that are closest to that point before you find the ones that are farther. So that's one way you can also look at it. Now, the opposite of this is depth first search. Now, there are three types of depth first search traversals. Again, these names, I'm including them because they are very popular, but I would prefer you try to understand how depth first search works in general, because there are many more than this, depending on how you do things. But the key thing with depth first search is depth first search goes depth first. It tries to go as deep as possible before coming back up, which is known as backtracking. Now, so the thing is with breadth first searches, so let's see what pre-order means. Let's see what pre-order traversal means. So with depth first search, right? The thing with depth first search is we start at the roots. Now, I want you to follow the direction at which the arrow is going as well. So now, if I go to the next node, I go to the left child, right? Because that's what I can see. But the thing with depth first search is that it keeps exploring that child. It doesn't go to the other child. It keeps exploring the child of B. So it explores the left child, which is A. Right? Now, it tries to continue at A. It doesn't have any children. What does it do at this point? It backtracks. It goes back to B. Now, that is where stacks come in, and that's where the recursion comes in. So you can think of it as this call, as F calling B, a recursive call, B calling A in a recursive call. Then A, when it's done, pops up the stack and backtracks to B. Backtracking simply means you are going back a path because the path you are going has no destination. So just think about it. Let's say we are in a maze, right? And you are trying to locate the ending of the maze. You don't know where the ending is. What do? You just start walking in a direction, right? If it's only one path you are on, you are good. Now, when you see a divergence, then now you have to make a choice. Do I go left or right? Now, I could go left and I could get to my destination, or I could go left and I could get trapped. Now, if I get trapped, if I go left, I need to come back to that point. So I'll probably maybe just leave a breadcrumb and go left. And then I'll come back to that point if I don't see anything and go right. That is the basic thing. But essentially, if you keep doing that operation, where if you see an intersection, you drop a breadcrumb and go the other direction and come back and go to the other direction, you eventually get your answer out of the maze. So it's essentially what depth first search is doing. It's just saying, okay, when I discover a node, especially with recursive depth first search, when I discover a node, I want to try and explore that node as quickly as possible and see how deep I can go. Then when I can't go as deep as possible, I come back up to find another way. So if you kind of look at it, it comes back here now. It's at B. When we get to B, when we get to A, sorry, we are A now, we backtrack to B. Now we go to D because we are done with A. Notice that we've not finished with B and we've not finished with F because they are in the stack. They are in the recursive stack. We are not done with them, but we are done with A because we've returned from A. Now, when you come to D, it goes to C, right? Because it's trying to explore as deep as possible. Now, when it comes to C, it sees that, okay, we are done here. Goes to E, which is the right side of D. Goes back to D and goes to E. Right. When it gets to E, it sees that there's nothing there. Now it backtracks to D. It's done with D at this point. Backtracks to B. It's done with B at this point. Now backtracks to F, which continues on the right side, which is G. And then from then it continues to I. All right. And then it continues to H. When it gets to H, there's no more place to go through. Backtracks because it's done with H. It's done with I. It's done with G. And it's done with F. Now, you see this pattern of moving through the graph. All depth first searches do something like this. Now, what determines if it's pre-order, in-order, or post-order depends on when you do the work you want to do at that node. So pre-order means do the work at this node now, then go to my left and my right child. That's the roots before the children. Pre-order essentially means process the roots before the children. That's what pre-order means. In-order means process the roots in between the left child and the right child. Post-order means process the roots after you've processed the right and the left child. Left and the right child. So, but if you understand this visualization of how DFS works, like through a tree. Oh, no, try and reset it. If you understand the visualization of how DFS works through a tree. Okay. If you understand the visualization of how DFS works through a tree, like this. So you notice that if you look at the arrow, right? We've seen the arrow now. Now, but with pre-order, when we saw F, right? We are doing the work at F immediately before we go to the left and the right child. We go to the right child, do the work. We go to the left child, do the work. Because it doesn't have left hand, we backtrack and do the work. So essentially with pre-order, we are processing the notes as we see them. We are doing whatever work we want to do as we see them. That's essentially what pre-order is. But the depth first search part of going down, backtracking is the same thing. It just depends on when we are doing what. So same thing with D, go to C, come to E, backtrack to D, backtrack to B, CG, CI, and CH. So this is essentially like how the pre-order works. Is this clear? Do you have questions? Thumbs up if you are good, thumbs down if you are not. Okay, I see some folks are still not clear. So the thing is, okay. Okay, let me see. So the thing with pre-order is I will give a formula that you can use to understand it if you really want to get the order. But to me, the order of the traverser is not important. It's really understanding what you do at different places. Okay, let me try something. Maybe I should do something. Okay, I'll come back to this. So let me go to the code here. I think this would help to clarify things. So if you look at pre-order, you notice that we are doing the same thing by traversing in each node. We are traversing the left and the right recursively. But with pre-order, we are doing something before we go to the left and the right. With in-order, we are doing something in between the left and the right. With post-order, we are doing something after we've gone to the left and the right. So this is kind of the difference between them. But essentially, they do the same thing. They're trying to traverse the graph in a certain order. And typically, to be honest, unless they say, what is the pre-order traversal of this tree? What is the post-order? What is the in-order? It really doesn't matter how you do it. But the key thing you need to understand is that the in-order traversal is a sorted traversal. That's the key thing you need to understand. Because if you look at the definition of a tree, all the nodes to the left are less than this node. All the nodes to the right are greater than this node. So if I process the nodes that are left are less than, and I process the nodes and I process myself and I process the nodes that are greater than, I get a sorted order. I'll go back to the traversals. I want us to just understand this thing before we continue the other traversals. We'll still go over them. I'm still going back to them. Let's just clear off, like, I thought there was some like confusion around it. So here we are. So that's pre-order. That we just see. Now, for pre-order, what you do is you perform a base case. Then you do your operations. Then you call the recursive function on the left node and recursive function on the right node. Now, we talked about recursion earlier. We'll still do recursions later. So that's why I don't want to go too deep into recursion for now. But I want you to understand that this is how like pre-order works. Now, with in-order is slightly different. The traversal orders are the same. Like in that, we go from the left to the root and keep exploring the paths. But now it depends on where we do things. So I think this will make it clearer. So we start from F. You notice that we didn't add F to our result here. Because before we do anything to F, we need to explore the left and the right child, the left child. So when we explore the left child, then we'll do something to F because it's in order. Now, when we get to B, we don't add B to our result because we are not doing anything yet. We want to still explore the left child and C. Now, when we get to A, because A has no left child, it tries to explore A's right. A has no right child. So it tries to explore A's left child. A has no left child. It explores A's right. A's right has no right child. And then it backtracks to B. Now, because we've explored the left of B, now we can explore B itself. Because we've explored what is on the left. Now we explore B. Now, after exploring B, we need to go to the right of B. Notice that F is still in the stack. We are keeping F in the stack. We're not yet back to F. We need to explore what's in the right of B. Now, at the right of B, we see D. But we can't explore D yet because D has a left child. We need to go see what's in the left child first. So we get to the left child of D. Because it's a leaf node, we are able to process it and come back to D, process D, then go to E. Go to the right child of D, which is E. Now we are able to process E now and backtrack to D, right? Now when we backtrack to D now, we can now backtrack to B. And then go back till we get to F and process F because we've processed everything on the left child of F. Now we've processed F now and we go to the right child. But F is still in the stack because we're not yet done. So now on the right child, we try to process G. Because G has no left child, that's why we process G now. But ideally we went left, found nothing, process G. Now we've added G, now we are going to the right. We go to the right. Now because I has a left child, we have to go process the left child first, which is H, backtrack to I. Because we process the left child, now we can add I. And then we can just backtrack to G we are done. Backtrack to F, and we're done. So if you notice this in order, it gives you the sorted order. And that's the key thing to understand. In order gives you the sorted order. Because if you look at it, if you process the left and process myself and process the right, everybody on the left is less than me, then everybody on the right is greater than me. So if I do that and I do it recursively, I'll get a sorted order. So this is in order, like essentially it's almost the same thing, but if you look at the code here, what we are just doing here is we are doing the work, which is console.log, in between the left traversal and the right traversal. Now, post order is just the opposite of pre-order, essentially. Instead of doing the parent first, we do the children first, then go back to the parent. So do we have any questions with in order before we go to post order? So with in order pseudocode, essentially it's the same thing as the pre-order. We just shift when we perform the operations on the node. So it says, can processing be done right before left, or it must be left first? So this is the thing. In order, post order, they define when you should do what. When an actual question, you have to determine which one you want to do first, depending on what you're trying to solve. But it doesn't really matter like which you do first, as long as you pick the right one. It's just arbitrary, just an arbitrary way to go through the graph. And as you can see, depth first search as a whole has a lot of orderings in the graph, in the tree. I keep using graph in the tree. So, and that's one key thing, because the orderings could differ in terms of depth first or breadth first. But understanding the general concept and knowing that, okay, you're explaining all the nodes, but then choosing when you want to do your work during the exploration, it was important. So any questions on that before we go forward? Before we go to post order? Okay. So for post order, essentially is the opposite of pre-order. Now, this is kind of the hardest to kind of wrap around, because it's funny in a way. At least for me, it took me some time before I was able to understand this. But this is the thing, you can look at it like this. Okay, you are at a particular node. So let's say we are at node F, right? We can't do anything to F. We need to go process all the left children first, and process all the right children first before we get to F. So what does that tell us about F? It means F will be the last node, right? Exactly. So in a post-order traversal, the root node is always the last. In a pre-order traversal, the root node is the first, because you're processing it first. So let's start with F. Now we go to B. B still has children. We need to go process B's left and B's right first. We go to A, right? A doesn't have any children. A doesn't have any children. So technically, you process the left, see nothing. Process the right, see nothing, then process A. But in this case, you have A because you're done with A, because you can't see anything. We backtrack to B, but we can't process B yet. We have to go to D and process D before we can. So I can see some hands are raised in the queue. I will come back to the queue. I just want to finish explaining this. So we backtrack to B and D, right? Now when we get to D, D has left and right children, so we have to go process them first. So we have to go to C. Because C is a leaf node, we are done with C. Then we go to the right side of D, which is E. E is a leaf node, we are done with E. Right. Now when we now backtrack to D, right? When we backtrack to D, you notice that now we can process D. And this is key to understand when you are visiting every node. There are 3 times you visit a node. When you first hit the node, when you come back from the left child, when you backtrack from the left child, and when you backtrack from the right child. Those are the 3 times you can process a node, generally in recursive traversal for trees. So now we are D, now we can process D. Now, when we backtrack back to B, because we've processed everything on the left subtree and on the right subtree, we can now process B. And then backtrack to F. But we can't process F because we're not done with the right child. So we need to go to the right child. Now we get to G. G has no left child, but we need to go to the right child. since left child is nothing, so we go to the right child. When we get to I, we need to go to the left child and the right child first. So we go to H. H is a leaf node. We process it. Now, I has no right child, so now we can process I. But technically, it goes to I, finds the right child, sees nothing, backtracks to I, and processes it. Then when we go back now to G, we can process G, and then we can process F. You can kind of see that is the opposite of the in order in a way. Now, so this is the thing, right? There are many ways you can do this traversal. You can do it root left, right. You can do it left, root, right. You can do it left, right, root. You can invert it and say right, root, left. It doesn't matter. Just understanding how the traversal work is more important than what post order is and what in order is and what all those things are. Because frankly, except maybe they will say find the in order traversal of the tree or find the post order traversal of the tree, those questions are usually explicit. Or find the kth position in a tree. So I would say the in order is usually the most useful, but the rest are not really asked that much. But it doesn't hurt to know them. Okay. So do you have questions on post order before we move forward? So we post order the same thing, but we perform the operation at node at the bottom. Okay, so folks that have questions, Nasif, I think you have a question. Go for it.
Yeah, sorry, I don't have a question. I wanted to put the time up, and
okay.
Yeah.
That's fine. That's fine. Okay, that's fine.
Yeah, Sheyi, thank you so much. Like, this has been a very, very, very amazing session. I'm just following you like bumper to bumper, basically, and I really understand. So what I wanted to say was, when someone was asking that when are we going to be using, like, how does this apply? Like, how are we going to use it like on your job role? So I wanted to say there because you already answered the question. Like, if you are building for scalability, and it also depends on where you work, and if you are doing so where I work, right? We normally do we do code review before your code is being sent to, we call it QA or TCO, Testing Center of Excellence. So before it goes there, right, you are meant to sit down with other senior engineers, then look at it. So besides that, our engineering manager, we have this documentation where we review, like, we have something we call software engineering practices and ethics, right? There's a way you are meant to structure your code. There's a way you are meant to solve problem. There's a way you are meant to arrange your code blocks. So if you are using an algorithm, all these things, it really depends on when you work. That's number one question. And two is that if you are, so our own goal where I work will be for scalability. That we don't want to know like the current customer base that are using the application. So whatever happens in the future, maybe it's going to triple or so, we have to like already factor that in our application. So we have coding standard basically, and they review those practices. So it's not how you say, okay, you implemented a functionality on an application, right? And once you implement it, you have called an API, you have connected to database, and everything is done. It has completed there. No, it's not yet done, right? Because even after the code review, before it still goes to that QA, the engineering manager will still look at what you have done, right? And it's going to be like rigorous testing. You're going to write unit tests for whatever application you have built before it now goes to that place. So once it goes there, they pair with the software tester that's going to test that implementation. So you guys will work together till everything is done. Then it can now go like to we call them apps management or DevOps. So that's just it. So it really depends on where you work. But this thing it's very, very, very useful. Very, very useful. And it's not just and again, it's not just about like maybe you are doing front end or back end. So far as software engineer, the rule is good for everyone. Like, you just have to follow those standards. So I just advise that we not over engineer stuff and stuff. So that's just it. Thank you.
Yeah. Thank you very much for that contribution. That was very insightful. So just to add to what you said, I've been in different teams from my personal experience, and there's a particular team I was working in that were processing web requests, and they needed some certain agreement on how fast the web request to be processed. So for those kind of applications now, like using the right data structure was very important, because I recall there was a time we're using a certain type of data structure, a certain variation of a hash map, and then we had to change it to another type of data structure just to increase the speed. So in that case, it's very important. Now I've worked on some other things, which I'm currently working now, where it's more like an SRE rule, like an infra rule. Now, when it comes to infra rules, like maybe when you're automating things, we don't really care, especially if it's not on the business logic side of things. If it's not the customer part of things, maybe just on the infra. These things are much more relaxed. People don't really care. Okay, let's say you are automating database backups every night, for instance. We don't care if you do N square and it takes more time. It's not really significant because it's not the customer part. But things that are generally on the customer part are very critical. Like if a customer sends a request and they are waiting for a response, you have to make that thing as fast as possible. So it really depends on where you work and what you're doing, and yeah. So, but it's good to know these things because it really helps like make you understand stuff and really opens a lot of opportunities up if you really understand these things as well. Okay. So, any other questions before we go on to graphs? So, graphs are kind of the most personally. This is my favorite data structure. Graphs are how we represent things, arbitrary things. So now if we look at all what we've had, for the tree, we had the roots, we had the left, we had the right, or we had root and children. With the graph, there's no order. A node can have 10 children, can have 2 children, can have 3 children, can have cycles, can have anything. Any arbitrary connection is possible with graphs. So the thing with graphs is you can use to represent anything. So let's look at a Facebook social network where you have friends and friends and friends and friends of friends and everything, right? You kind of have a social network like this, and you can represent maybe a connection between two people as them being friends of each other. And if you have a one-directional connection, that means this person is my friend, but I'm not his friend, or something like that. So you can use to model social networks. You can use to model a road network, like let's say the roads in Lagos. You can use to model the roads. So maybe you can model like the road with it. You can even use to model a country map. I can use to model the Nigerian map to do things. I mean, those of you that are familiar with graph databases, you may kind of understand where I'm coming from. But with graph databases, you can define any relationship. You don't really have like defined relationship between anything, like SQL. You don't have any relationship can be related to anything. Now, in terms of like the bottom one, this is machine learning, this is neural networks. Neural networks are essentially graphs. And graphs are very applicable. Not directly, but usually they're applicable. Like I've worked with situations where I've had to build graphs like of things. Not that I'm really writing the logic for building the graph, but I need to understand how the graph works and implement dependencies. So graphs can be used to model anything. Like they are very versatile. And you might have guessed, or a linked list is a variation of a graph. A tree is a variation of a graph. But the graph extends the concept to anything. So technically, what's a graph? So a graph is made up of a finite set of vertices, which are connected by a set of edges. So remember in trees, we said they were nodes, right? In graphs, we call them vertices, but they're essentially the same thing. And E are the edges, which is the connection between the graphs. So what do I mean? This is a graph, for instance. I is a node, is a vertex. 5 is a vertex. The connection between 1 and 5 is an edge between 1 and 5. So, like I said, the vertex is the fundamental unit of graph. That's what you use to store a graph node. That's what essentially what a graph node is. Now, an edge is the connection between two vertices. Now, a path is a sequence of vertices going from one vertex to another. So, what do I mean? 4, 1, 5 is one part of the graph. 5, 3, 0 is one part of the graph. 5 to 7 is a part of the graph. You can see that these are very arbitrary now. There's really no structure. You can start from anywhere and go through things. Now, so the thing is, a degree of a vertex is the number of edges connecting the vertex in an undirected graph. Now, there's something we call directed and undirected graph. Is that a question for me? (460). What is 460? Oh, I see what you mean. I see what you mean. So 460, yes. So 460 is a path. Yes. 460 is a path. So in a graph, you can have almost an infinite number. It's not infinite, but it's a lot of paths you can have. And the path can start from anywhere and end at anywhere. That's the path. So the degree of a vertex is the number of edges connecting in a non-directed graph. Number of edges connecting a vertex in a non-directed graph. Now, there's a difference between a directed graph and a non-directed graph. A non-directed graph has no notion of direction. So if I have an edge to you, you implicitly have an edge to me, basically. So it's kind of like saying you have a road between two cities. If one city can reach a city by road, then that other city can reach the other city back by that same road. Now, a directed graph is different. So if you have a one-way, for instance, that's a directed graph. It means you can go one direction, but you can't go back the opposite direction. So usually you use directed graphs to model like sequences, like when you have an operation that depends on another operation, you can model them with graphs. And usually like in a lot of places where you have to do computations, where you have to write some business logic that depends on the business logic that depends on that business logic. Usually you have like a framework that uses some form of graph to define these things and executes them. Okay, so yeah, so out degree. So the concept of in degree and out degree are only applicable to directed graphs, because in directed graphs now the in degree is the number of incoming edges. Remember, in a non-directed graph, the incoming and the outgoing are the same thing. So there's no distinction. But in a directed graph, we have an in degree and an out degree. Out degree are the number of outgoing edges, number of outgoing edges of a vertex in directed graph. So a cycle now is a value path starting and ending at the same vertex. So a cycle can be from 1, 0, 6, 4, 1. That's a cycle. 1, 0, 3, 5, 1. That's a cycle. Now, graphs allow cycles, and cycles can occur anywhere. But trees are graphs that don't have cycles. That's the distinction. Okay, so let's see this visualization here. Okay, so this is essentially a graph. You can have a graph of anything. Here. Now, this is an undirected and unweighted graph, which means that the graph has no direction, it's bidirectional, and it's not weighted. So you can have a concept of weights now, which means the edges have some cost associated with it. So for instance, if you are modeling cities now, the edges could be the distance between the two cities. The edge weight can be the distance between the two cities, or it can be the speed limit between the two cities. So you can see that you can use to model things and assign like weightages to those connections as well. So this is an unweighted, undirected graph. This is an undirected weighted graph. So you can see that from 1 to 3 now, if you go from 1 to 3, it will cost you 120. If you go from 1 to 0, it will cost you 50. So you see that adding weights to the graph makes it a weighted graph. Then you have a directed, unweighted graph, which is a graph that has direction, right? And then you have a directed, weighted graph, which is a graph that has direction and is weighted. So depending on the problem you are modeling, you need to use one of these. Now, so what are the applications of a graph? Excuse me. Social networks. You can use to model maps. Then your web crawlers are graphs. Essentially, what's like all these web crawlers, like that big organizations run to crawl things, they use a graph. So how do they do it? They start at the root of the website and store it in a queue. Then they explore all the links on that page. So they pass the page, find all the links, add them to the queue. They move to the next item in the queue, find everything linked to that and add it to the queue. So they keep doing that as they're processing. That's how web crawlers essentially work. The internet is essentially a graph. Computer networks are a graph. Computer networking, they are graphs. Routers are not their own graphs. Recommendation engines are graphs. Neural networks are graphs. So graphs are very versatile. They can model anything. They can model a lot of things. And so we've seen directed graphs and undirected graphs. And weighted directed and weighted undirected. So this is an undirected unweighted graph. The undirected weighted graph, we saw this earlier. A directed unweighted graph, and then a directed weighted graph. So some other things to note are trees are undirected graphs with no cycles, which are all connected. So for a tree with n nodes, there will be n minus 1 edges. So trees are a variation of graphs. Then you have rooted trees. So rooted trees are what you've seen earlier, where you have where each node points to child nodes. Where you have like a concept of the roots and there's no cycle. That's what we saw earlier with binary trees and all those trees. Now, there's a special type of graph called a directed acyclic graph, which is important. We will not have time to go into it today. But this is when you have the roots. It's a directed graph without cycles. Meaning that when you're trying to model, like, say, some sequence that depends on the sequence that depends on the sequence that depends on the sequence. Now, you can have an arbitrary graph that gets complicated. But if you want to know which sequence should I do first, then you have to be the directed graph of that, right? And then you start like doing a graph traversal to see which items are ready to be processed. You can use breadth search, you can use depth search. But these are just some applications. Now, the key reason why I like graphs is this. Graph algorithms are complicated. They are not really easy to come up with. So essentially, once you can model a problem as a graph, you just need to apply one of the algorithms. Once you know them, you don't need to start coming up with, okay, this is a sliding window or this is this or that. With graphs, it's straightforward. Once you can think of how to model the problem as a graph, you just need to apply one of the algorithms, either breadth first search or depth first search to find what you need. Okay, so again, this is just a review of trees to see that how graphs are so similar to trees. And everything we apply to trees also applies to graphs with subtle differences. Okay, any question on graphs before we go to the representation? Our brains fried. Do you want to take like a 2 or 3 minutes break and come back? Okay, I'll assume we will continue then. So, okay, let's write on. So to represent graphs, we have multiple ways of representing graphs. There's the edge list. Okay, so we want to take a break. Okay, so let's take a break and come back at 1:48. 5 minutes break. Okay. See you guys at 1:48.
Hello, please. Are we done with this session? I can't hear anything again. So I don't know if it's only for my end or it applies to everyone as well.
Okay, so we are currently on break and we are going to continue soon. Yeah.
All right. Thank you so much. Drinking water.
Okay, so are we all refreshed? Got some water. Took a quick nap. Let me see. Okay, yeah. So somebody, I guess that's a mistake. Someone wanted to write thumbs up, but that's fine. Okay. So yeah, it's good to graph water. Nice. So yeah, it's good for us to just take a break and because I know this is actually a lot, especially if you're seeing this for the first time, it's really a lot. And I'll be honest, like this graph thing is a lot. It's a lot more than this. But I'm just trying to cover the fundamentals so that we can at least be able to branch off on our own. So ways to represent graphs. So the first way is using an edge list. So I think this is better shown with an example because it's easier to get it when you see an example. So using an edge list, basically you have a list of edges in the graph. This is what it means. So let's say I have the graph on the left and I want to represent that graph in the system, right? Like visually, I can see that is what it is. But on the computer, it can't see that. It's either you represent it as an array or as a link structure. Those are the two things. So in this case, you're using an array. We're using an array of arrays in a way to represent the edges. So you can see on the first line, we have an edge between A and B, which is this one. Then we have an edge between A and C, which is this one. Or an edge between B and C, which is C and B, which is this one. Now, this assumes that this graph is a non-directed graph. If it were a directed graph, then you will have like what duplicate edges. But it depends on what the question specifies, so it depends on how they give you the inputs. But it's arbitrary how you want to set it up. But this is what an edge list essentially is. So this is the notation, and the edges don't follow any particular order. They are anyhow. So you can kind of see some disadvantages with this, right? If you want to add an edge to the graph, it's pretty easy. You just add an entry to the list, right? But if you want to find all the edges connected, so there are two key operations to do on the graph. Find the vertex and find all the neighbors of the vertex. Those are the two key things you do. Remember in tree traversal, at a node, you go to the left and the right. Or at a graph, because you don't really have a notion of left and right, you really have a notion of neighbors. You don't even have a notion of children, just a notion of node and the neighbors. So you want to be able to access a node and go to the neighbors. Those are the key things you do in a graph. Those are the operations you do in a graph. So with an edge list, that makes it difficult because if you want to see if a node exists, you kind of have to go through the whole list, right? So it has its disadvantages. So let's move on to the next one. So usually they give you this in form of questions. You don't usually use it to solve anything. Now, an adjacency matrix. Franklin, go for it.
Oh yeah, good day. Sorry for taking you back. I'm
Sure.
not really connected to the lecture, but then I've been throwing a question here. I would like to join the Slack group. I missed some session when the program started, so
Yeah.
I think that's why. So is there a way I can still join?
Yeah, I think the organizers would have a way for you to join. They would, yeah, you said you should check your email. Check your email.
Okay, thank you very much.
Yeah, no problem. Okay, so yeah, so now for the adjacency matrix, essentially what we do is you do rows at the vertices and the columns at the vertices. And then if there's an edge between a row and a column and if there's an edge between two vertices, you match the corresponding row and column. It's easier with an example. So this is a graph we want to model in this adjacency matrix, right? And this is the modeling. So you see these nodes at the top, 0, 1, 2, 3, 4, they correspond to all the nodes. So 0, 0 is the connection between node 0 and itself. 0, 1 is the connection between node 0 to 1. 1, 0 is the connection between node 1 to 0. So let's look at 3 and 4. So 3, 4 has 1 here. All right. But 4, 3 does not have anything because it's a directed connection. You see the thing? 2, 3 has a connection. So 2, 3 has a connection. 1, 2, 1, 2 has a connection here. Now 0, 2 is unique because you have 0, 2, but you also have 2, 0 for the reverse connection. So this is how you use an adjacency matrix to store it. Now here I'm storing 1 and 0. If your edges had weights, you could store the weights here instead of 1 or 0. But if it's not weighted, you just indicate it. Now, a good advantage of this type of approaches is good for when you have dense graphs. Because if you notice, so let's say I had only, if you notice in this graph, I don't have a lot of 1s in this graph. I have a bunch of 0s here. That's because the graph is sparse. If it's a dense graph where every node has a connection with every other node, then this would be a good representation. But for now, it's just a waste of space because all these 0, 0, 0, 0 are just waste of spaces. Now, and the key thing to notice, most graphs you encounter in real world applications, they are sparse graphs. They are not dense graphs. Like if you look at Facebook now, how many friends connections do you have? Everybody's not a friend of everybody. You only have maybe some friends and other friends. If you look at the graph is sparse. But the number of nodes that day. And this happens a lot, generally. The graphs are generally sparse. Now, an adjacency list is an optimization of this, right? So instead of storing vertices edges that we don't use, let's only store the ones we need, right? And that is where you have a hash map. So use the hash map to store the vertices. And then within the hash map, you have the value is a list of the neighbors or the outgoing vertices. So what do I mean? This is an adjacency list. You have the nodes A, B, C, D, E as keys in the hash map. Then as values, you have the connection. So A to C, B to C, C to A and D, D to E, and E doesn't have any outgoing edge. So this is an adjacency list example. This is very efficient. Now there's another one called adjacency map. It's essentially the adjacency list, except that instead of using the list here, you use a map. Now the reason why a map is good is that you can check for neighborship. If you can check if an element is a neighbor in constant time without scanning through the whole list. Now you see the difference, you see where the advantages of set come into play and how knowing how to use the right data structure is important. Now, typically you won't see this if most people just use adjacency lists, but this is actually a more efficient representation of it because you can then have an O of 1 lookup when you're finding neighbors that are connected instead of having an O of n lookup. So this is the adjacency map example. Same thing, it's just that instead of list, we use a map. And this is another example here. So we use a map to store the list. So this is 1, 2. So in this case, we are using like the indices. So this is 0, 1, 2, 3, 4, like that to store it. And then we have the corresponding values. So now for graph operations, right? So someone asked a question. This person said, what's the time complexity of DFS and BFS? Now for a tree, is the number of nodes in a tree. Because if you look at what you're doing in BFS or DFS, you are traversing all the nodes at least once. So that's O of n. You can say, okay, maybe I go and I traverse it 2 times, 3 times, O of 2 and O of 3 and O of 4, it doesn't matter, it's O of n. Now for a graph, right? When you're exploring a graph, right, you're exploring all the vertices and edges at least once. So it's V plus E, which is vertices plus edges. That's the time complexity of DFS or BFS for a graph. So if you think about the work you are doing, you can easily come up with that. So these are the different time complexities. I wouldn't worry too much about, like you can look at this later, but essentially, adjacency map is the most efficient. So if you kind of think of what you need to do, if you need to use a structure, then you kind of see why it's like that. So let's look at add vertex. If I have an edge list, it's just a list of edges, right? I just need to add that edge. But the problem is I also need to go look for the corresponding edge is there and add it. So this is why it's O of E. Actually, hold on. I backtrack on that. Add a vertex. Let me see. So if I'm adding a vertex, wait 1 second. I think this is wrong. Wait, I think that is wrong. So if I add a vertex between A and B, I add another A and B. Oh, add a vertex. Okay, I see the reason why. So adding a vertex is not adding an edge. I was confusing the two. So adding a vertex, you need to add a vertex and you need to make a connection to other elements that might need to have that vertex. So it's O of E, yeah. O of E. Removing a vertex 2 is the same thing because you have to go through everything to remove it. Add an edge is easy, which is O of 1. This is what I was confusing you with earlier. Removing an edge is difficult, which is O of E. So you can see E here is the number of edges. B is the number of vertices. So from this time complexity, there are different things, but I'll just, if I were you, I'll focus more on the adjacency map and the adjacency matrix. Those are the two things I'll focus on. Now you can see the problem with the matrix here. If you want to get the neighbors of each of them, you have to go through the entire line, which is the entire row or the entire column. That's why it's O of V. But here you just need to go through the neighbors you want, which is O of degree of U means the number of neighbors, essentially. So yeah, I think we can go through this later. I don't want to spend too much time on this. Any questions? Any specific questions on this before we go to the traversals? Are we still alive?
Okay. You're alive. Bro.
Okay. I want that to be sure because I know folks might be getting tired now. But I'm trying to wrap up. We'll soon be done. Once we do with the traversals, it should be straightforward now. What is an edge? So the edge is the connection between two vertices. So look at this graph here. 1 is a vertex, 2 is a vertex. This connection between 1 and 2 is an edge. The connection between 2 and 3 is an edge. The connection between 1 and 3 is an edge. So vertex is a node, yes. Assuming, okay. Don't worry, we'll soon be done. We'll soon get to the show. Edge is a path between two nodes. Edge is a path between two nodes. Yes, edge is a path between two nodes, yes. If it's just between two directly connected nodes. Let's put it that way, yes. Between two directly connected nodes. Because two nodes, you could traverse a lot of paths. And that's not an edge. An edge is just one hop, like one point between two nodes. If they're directly connected, yes, then that's an edge. Yeah. Graph traversals. So it's the same thing, BFS or DFS. Now, the BFS you are doing for graphs is similar to what we do for trees, except that because we have cycles, we have to keep track of what we've seen and what we've not seen. That is the difference, the main difference. Now, so it's the same thing. You start at the graph, explore the immediate neighbors first, explore the next level, and use a queue to keep track of the traversal. So now the thing is, this is a BFS traversal, but there are multiple others depending on which nodes are visited first. In the interest of time, I will just skim through this. I mean, you can go through it and see the details of the traversal later and the code. But essentially, what it does here is I try to find the. Okay, let me try and see if I can see. 1 second. I'll stop sharing. Let me check something. I think there's something in here. Okay, yes, we can do DFS and DFS here. What we can do here. Graph traversals. Making the graph too complicated. Let me just use a basic example. I want to use a very small graph. It's too much. Okay, let's use this graph for instance. This is not a good example, but 1 second. Okay, so let's pick a small graph, an undirected graph. An undirected graph, and let's pause and run BFS. Start from vertex. Let's start from vertex 0 and run BFS. The smallest graph I can find, run BFS. So with 0, right? This is visited. This is nodes we visited, and we are keeping track of the parents. But then if I skip forward, what happened? Full graph. What's happening here? Full graph. Start from 0 around BFS. Okay, step forward. So with 0, this is the queue on the left here. So with 0, I explore 2 and add it to the queue. But I'm also keeping track of it because I don't want to visit 2 again. Now we pop 0 is at the queue, right? So we take 0 off the queue. Okay, we add 3, sorry, and we have to add 4. Yeah, so we have to add all the neighbors of 0. Now we've added all those neighbors to the queue. Now we take 1, which is the next item in the queue. Now, because normally we want to add 0 again, right? But because 0 okay. Can you guys see my screen at all?
Yes, we can, sir.
Okay. So, but because 0 is already in the graph, we won't go back to 0. So now we have to add all the neighbors of 1 again. All right. So add all the neighbors of 1. What do? We have to add 2 to the queue, but 2 is already in the queue, so we can't add it again to the queue. You see why? So this is why this is the key difference. You have to keep track of what you've seen before, so you don't keep adding, you don't loop around, because there could be loops in the graph. So the same thing to where we are with 2, we try to add 5. 5 is not there, we mark it as visited, add it to the queue. We add 6, 2, add it to the queue. Are we done with 1? Yeah, we're done with 1. Then we go to 2. And when we get to 2, we want to add 1, but we visited 1 already, so we don't want to go back to 1 again. We check for 4. We've added 4 to the queue already. We don't want to go there again because we visited it. We go to 6. 6 is already in the queue, and we visited it, so we'll just skip it. Then we'll pop up the next item from the queue, which is 3. So we go to 5. 5 is in the queue. We don't need to add it back again. Take out 3. We go to 4. 6. 2 is already visited. We don't care. 6 is already visited. We don't care. 7 is not there, so we add 7 to the queue. Go to 5. All the neighbors of 5 are already, we've already visited them. We're not adding anybody. We take out 5. Go to 6. All the neighbors have already been visited. Not adding anything. We take out 6. And we get to 7, we just take out 7. So that's essentially how the BFS works. Now the thing is, with BFS, you could have multiple traversals. It's not like a tree where you have a certain order. You can have multiple BFS orders depending on which node you visit first. And this is kind of the pseudocode for BFS. So it's almost the same thing. You initialize a set for tracking the visited vertices. You initialize a queue to track what you're traversing. You add the state vertex to visited. You enqueue the state vertex. Then while the queue is not empty, you dequeue a vertex. And for each neighbor of the vertex, right? For each neighbor of the vertex, if that neighbor has not been visited, then you add it to visited and enqueue the neighbor. So that's just the pseudocode for it. BFS, same thing we did for trees, except that we need to keep track of which nodes we visited and not visit them again. So you start an arbitrary node, you keep exploring that node till you get to the end, and then you backtrack and explore unvisited children. So you only backtrack and explore when you've not visited. If you visited it before, you just skip it. So time complexity is the same as BFS. Now this is one BFS. Actually, this is DFS, not BFS. I will change this title. It's misleading. So this is one DFS you can have. It's arbitrary. You can have a lot of DFS for a particular graph. It's arbitrary. You don't really have one order. And this is the pseudocode for the iterative DFS. The difference between this pseudocode for the iterative DFS and BFS is just that you use a stack instead of a queue. It's essentially the same code. You just use a stack here instead of a queue. Now for the recursive one, it's similar, except that if the neighbor has not been visited, then we'll make the recursive call. You know, previously we choose to just make the recursive call to the left and the right. But in this case, we check if the neighbor has not been visited before we make a recursive call. And we'll add them to the visited set once we visited them. So let me quickly see if I can find the graph traversal. Okay, breakfast. Okay. So let's try get first search with the undirected graph with this very small graph, new graph. Okay, so let's see this here. Want a good graph. Okay, let's use this type of graph. Good. So now I'm going to pause. Run DFS. Run DFS. Okay. Pause. What's the problem? Oh, state vertex should be 0 on DFS. Okay. So now we are starting our DFS from 0. When we step forward, we go to 3. We go to 3. Now, normally we'll add, if it's BFS, we'll have added all the neighbors to the queue before we start exploring. But with PFS that's not the case. With DFS, it's not the case. We go to 3 immediately. Immediately. But we add that 0, we've seen 0. From 3, we choose 1 to go to. We want to go back to 0, but 0 has been visited, so we can't go back. Then we try to go to 1, then we go to 1 immediately. We add 3 to the visited set, and then we go to 1. We continue for 1. We want to add 3 back, but 3 has already been visited. We don't want to look back. Then we go to 5. We go to 5 immediately. So we repeat this process of keep going to nodes that we've not visited, right? Until we finally explore the whole graph. I have some additional resources if you want to see this in more of an animation form. But yeah, this is how DFS works, essentially. So you see these recursive calls here. The recursive calls keep going. And when they finish, they will all backtrack to the end. Okay, we're done here. So that's essentially how DFS works. Yeah. Any questions before we continue with DFS and PFS on graphs? Now, I'll make a mention of other graph algorithms that we can have. We can have Dijkstra, Elman-Ford. There are a lot of graph algorithms, right? But most things you encounter DFS or BFS. Those are the most you encounter. At worst, you can learn Dijkstra if you really want to. But Dijkstra is almost the same thing as BFS, but instead of using a queue, use a priority queue, use a heap. The reason is, with a queue, you are selecting the next item, but with a heap, you are selecting the shortest item, like the closest item. So it's used when you are trying to find the shortest path between 2 places. So, but the thing with graph algorithms is you just need to learn them. Like Dijkstra, any algorithm that has a name to it, most likely you're not going to get asked. Like nobody's going to say, what is Dijkstra's algorithm? No. They can say, okay, they can give you a path and say, find the shortest path. And it can't really get more complicated than that. You have to use it to find the shortest path of some form. But again, most of the things you need to know on graphs, if you know BFS and BFS, like you've covered like most of what questions you can get on graphs. You can do it without learning the others. But if you want to learn, you can learn them. But DFS and BFS are a must to know very well. So I encourage you to try and practice it well, read it well, look at the extra resources I sent, and just try and take your time to get familiar with it. So there's another way we can represent graphs, which is using matrices. Now, matrices have a certain property because the matrices are already graphs on their own, in that the nodes are the cells and the edges are the connections between the cells. So for instance, this node here, it has 8 edges, depending on how you want to look at it. If you want to consider the diagonal edges, or 4 edges if you only want to consider the adjacent cells. So this is one way you can see graphs. They give you as a matrix and tell you, okay, do something on this matrix. using a graph algorithm. It's already implicitly represented as a graph. It's just like a maze. It's implicitly represented as a graph. You don't need to construct another graph. Other question can get if you how to apply DFS and yes, I'll go to some questions briefly. So this is matrices as a graph. When we do matrices, so this is the formula to getting the adjacent rows of a matrix. So you can go row minus 1 plus 1, column minus 1 plus 1, the entire combination. You can go through this later. So DFS versus DFS, which one is more applicable? So the key thing to notice is BFS is breadth first, DFS is depth first. Now, BFS is very useful for one particular problem, finding the shortest path. The reason is that it explores from the node going out. You can use DFS to find the shortest path, but you have to explore all the paths that are possible, which is a lot. So BFS is more efficient to find the shortest path. Now, all problems can be solved using DFS or BFS. That's the real truth. It's just that depending on the problem, one might be more efficient and one might be easier to implement. I'll add that to it. One might be easier to implement. But all problems can be solved with either. BFS is the queue, DFS is the stack. Now, there are two types of DFS. There's iterative DFS, there's recursive DFS. Recursive DFS is using recursion. Iterative DFS is using a stack. And it's similar to BFS by replacing the queue with the stack. That's the only difference between the two of them. So both can be used to traverse the whole graph. So if you want to traverse the whole graph, you can use any of them. BFS groups levels together as they radiate from the source. But DFS groups paths together. So if you want to find paths, if your algorithm is okay, find certain paths that meet this certain condition, then DFS is better. BFS can do it, but it's a little bit more work. So before I go into problem solving, I'll go over the exercises that I came up with. So I would say there's this book called Practical Algorithms and Data Structures. I would say you should read through the trees and the graph section. You can skip the AVL trees. Skip AVL trees, and for the graph, just read BFS and BFS. You don't need to go through the Dijkstra and topological sorting for now. Just to get the fundamental, read DFS and BFS. Once DFS and BFS are second nature to you, then you can go explore those other ones. Because all those other ones rely on DFS or BFS. And if you understand BFS, Dijkstra is going to be easier to understand. Because what you are doing with BFS is, when you're adding items to the queue, with Dijkstra, instead of using a queue, you're using a priority queue. And you're adding the items and the costs as you're going from the source and picking the lowest costs each time. That's the major difference between BFS and Dijkstra. In fact, Dijkstra becomes, if you use Dijkstra on a graph if you use Dijkstra on an unweighted graph, it becomes BFS, essentially. So this guy here, William Fissett, he has a lot of graph video playlists. And the thing I like about his graph videos are he uses a lot of animations. So you can actually visualize and see how it's going through. Then the other one I would say is, so you can focus on the first 6 videos. Then let's code binary tree explore card. So in this one, I would say focus on the editorials, understand the traversals, then solve questions you find interesting. Then binary search tree explore card. Same thing, read the editorials and solve questions you find interesting. Then the graph explore card, go through just the breadth first search and the depth first search. There are a lot of graph algorithms. We'll focus on DFS and BFS for now. Once you are good with DFS and BFS, you can move on to the others. But trust me, if you understand DFS and BFS, you can crack. You'll be fine with a lot of interviews. So resources I've shared before, grouping coding patterns and neat code. These grouping coding interview patterns is very good for like understanding the patterns between them. Then the visualizers I've used here, and then some additional readings if you want to read. So any questions before we go over the problem solving parts? Okay, so let's go to the problem solving. So for problem solving, right, the thing with trees is, with a tree, the problem is usually given as a tree. Like there's no way you can easily construct a tree like that. We'll talk about constructing trees with recursion, but that's different. But for trees, they will tell you this is a tree, find this. This is a tree, find this. They usually give the problem as a tree. Now for a graph, right? The problem So the problem with the tree is you have to know what you're looking for in the tree and how to use the different traversals to get what you want. Either you are going left, right route, or left route, right, or what you are processing, what you are sending when you are doing the recursive calls, or you are returning from the recursive calls. Those are where you need to like pay attention to. But for the graphs, it's not usually explicitly given that it's a graph. You need to think about how the problem can be modeled as a graph. They won't tell you that this is a graph. They just give you a problem statement. So usually they'll give you a form of a matrix, or they'll give you some edge lists, or they'll just give you a random problem statement. So not explicitly given, but you need to think about how the problem can be modeled as a graph and apply one of the graph algorithms. So what key things to know DFS and PFS very well, very, very well. Okay, so because we are running out of time, I'll just go through this and explain the idea behind how to solve it, and I'll share the resources later. So binary tree level order traversal. This is essentially asking to, given the root of a binary tree, right, do a level order traversal. So essentially that asking to do a level order traversal here, which is using what? Using BFS. BFS gives you the level order. Now you can do it with DFS. In fact, let me go through the solution here. Connect. Okay, so this is level order traversal here. This is using BFS by grouping the nodes, and you can also do it too with DFS here by like passing the levels down and using it, storing it into a map. So again, most of these graph problems or tree problems, they have to do with understanding how to apply DFS and BFS. That is what they mainly focus on. So for this other one here, minimum depth of a binary tree. Yeah. So it's saying, given a binary tree, right, find its minimum depth. The minimum depth is number of nodes along the shortest path from the root node to the nearest leaf node. So in this case now, the minimum depth is 2. Because the root to this leaf node is 2. So they're looking for the shortest leaf node from the root node. That's what they are finding as depth here. So read the question, because the question will tell you what they think depth is and what depth is not. So in this case, it's about passing the depth down and incrementing the depth as I'm recursing to the left and as I'm recursing to the right. So this is BFS. But you can also do it with BFS, I believe. Yes, you can do it with BFS and DFS. So minimum depth, this is using BFS to do it. So with BFS, because BFS explores all the closest items first. So if you do a DFS, you will get your answer quicker than doing a DFS. Because with DFS, you have to explore all the paths. So this is the BFS solution, and this is the DFS solution. I just did this for these problems to make you understand that problems can be solved using either approach. If you really understand them very well, they can be solved using either approach. There are only a few problems I know that can only be solved with BFS, which is shortest path. That can be solved efficiently with BFS, which is shortest path. And for DFS, it has to do with like finding the paths. You can do it with BFS, but it's not very efficient because you have to store a lot of information. So for graphs, this is one example of a graph problem. Now, this problem is given as a matrix. But what they are saying is start at a point, right? So they are saying this is like water. Like 1 is water, 0 is land. So if this is water, right, like kind of fill all the other places with more water. So that's what they are doing. So this is 1. This is connected to 1, 1, 1, 1. So just fill it recursively with all the neighbors. So in this kind of thing, what are we doing? We are trying to do a graph search problem. So if you start from here, if you do a BFS or a DFS, you can explore everything that is connected to this. So you just need to do a DFS and BFS, find everything and apply what you want to apply. So I think this solution here is a DFS solution. Yeah. You could have used BFS for this, but DFS is usually easier to write. The recursive one is easier to write. It's easier to write and more intuitive. But either one is fine. You can use BFS too as well. It doesn't matter. You're just trying to explore the graph. Therefore, this one, number of islands, this is a classic problem. Essentially, what they are saying is you have a grid. 1 is water, 0 is land. Find the number of islands. In this case, it's 1 island because they are all connected. But if you come here, this is 1 island. Yeah. This is 1 island. 1, 1, and 1, 1 is 1 island. This is 1 island, and this is 1 island. So what do you do in this type of problem? You go through them. Once you see a 1, You do a BFS to find all the other islands that are connected. So if you start from here, for instance, now you do a BFS, you will discover this, this, and this. That's one island. If you start here and do a BFS or DFS, you discover only this. If you start here and do a BFS or DFS, you discover this and this. And I think I have the solution to here. Yeah. So that is really it about grass. Once you understand BFS or DFS, it's easy to just know, okay, I will just apply this, I'll just apply this, I'll just apply this for majority of the problems. Yeah. So there's one thing I would say you should focus on really knowing is DFS and BFS. That is, you can't escape it. If you are doing like a serious coding interview, you can't really escape it. The solution stroke, you know, maybe when you, I think now it's because brains are fried. When you relax and you take some drinks and enjoy yourself, then it's probably stick clear. All right. So I think that's everything I had for today, unless somebody has any other questions. We can call it a day. Thanks for staying till the end. I know this is one of the most trees and graphs are one of the most difficult concepts to really understand. So yeah, I think they're one of the most hardest data structures to understand. But once you understand them, it becomes easy to solve problems. Okay. So if there are no other questions, I'll hand it over back now to Shay. So a question: how can someone get a paid mentor in order to fast track his growth? I'm not sure I have an answer to that question. I think you just reach out to people you think can be a mentor to you and see what they see or something like that. Or that's what I would just see. A paid mentor. Okay, paid mentor. I think there are websites you can go to, like Code Mentor, where you can pay for someone to like look at the problem you have. I think there are websites like that. Yes, there are websites like that. Can we get a free account for educative.io? I don't know about that. Maybe talk to the organizers. It's possible. It's been a great time here today. Yeah, I enjoyed this session as well. Thanks everyone for sticking around. Okay.
Yeah.
Go for it.
Okay, yeah. So thank you so much. Like we really appreciate your time. And thank you to everyone for joining us today. And please don't forget to fill the feedback form. I just dropped it in the chat box now. It's really important, please. It helps us to improve the bootcamp. Or if you have friends too that you think they might need this, please tell them to join. You can share the link with them to join us. So next week we are going to be starting with algorithms. Please tell your friends that needs this. It's getting more exciting. This is where we are actually going to solving more problems. So please, we're looking forward to seeing you guys next week. And if you have any questions, please let's make use of the Slack channel. And I will be sharing these recordings via email to everyone. And if you have any questions, please don't forget. The Slack channel is the best place for us to communicate and all. So thank you so much, everyone. Thanks to our great. Let's appreciate our great speaker today. And yeah, thank you so much, and thank you so much, everyone. And see you guys on the next call. And have a great evening.
Thank you, everyone. Bye.